and you opt into treatments where you know that your U is high, that you get a good outcome. So they tackle this question directly and have all the notations for it. So that would be the place to look. But for our purposes, the way you said it is rigorous. Use independent of X. Yeah. So that's the Chernyshkov-Ensign, Konachika, 2004, I want to say. Yeah. Okay, now how do you estimate these things? So, yeah.
When you're setting up these way of generating the Y
Yeah.
conditional domains, just how do I think about the restrictions that I need to impose on the Q, U, Y of X so that it's a legit way of generating it? I mean, it seems like analogous to the conditional distributions, I have some sort of monotonicity.
Yeah. Yeah.
But just like say, if I had never thought about this and I just like want to generate a joint of
Yeah.
X in this way
Yeah.
via this quantum function, just remind me, what are the restrictions that I need to impose on you so that I have something valid?
So the issue is going to be with the contraction function. If you're trying to use this to spit out the well, okay, think about it from an estimation perspective. So if the support is infinite and the lines are not parallel, they have to cross somewhere. Yeah. So that's going to be not valid. That's a problem. That's a problem. And so you can impose that they don't cross. But then that of course means you need finite support. And then if you want to generate data with a contraction function that's linear, then again that means you need to have a finite support. Yeah. Which is also another reason why in this, there's no way that the contraction functions are linear. But yeah, we're going to get there in a second. Okay, how to estimate these things. So, we had the least squares loss function for OLS. If I'm doing OLS, then I have my squared error objective. Now I'm going to do quantile regression. So for median regression, for instance, I'm going to have the absolute value loss. And if I have, but more generally, if I'm looking for a different quantile, then I'm going to tilt. I'm going to tilt the absolute value loss to penalize more positive errors than negative errors, so that I allow, let's say, if I want the 25th percentile, 3/4 of the errors to be positive because they're penalized by 1/3, as opposed to by 1/4, and only 1/4 of the errors to be positive. So. We can do a very easy perturbation exercise to think about why that makes sense. So suppose I want, forget about conditioning. 1, 2, 3, 4, 5 in my set. And I'm trying to use this objective. So y1 equals 1, y2 equals 2, all the way to y5 equals 5. And I'm trying to find the median. So if this is my median, clearly is 3. And then what's the sum of penalties? The guy 1 away gets penalized by 1. The guy 2 away gets penalized by 2. And so that's I sum these, so this is 1, this is 2. I sum these to get the objective function I'm trying to minimize. If I perturb and if I try to have 2 as the median, what cost would I pay? I would pay a cost of 1 here. I would pay a cost of 1 here, a cost of 2 here, and then a cost of 3 here. So I would pay a higher cost. So clearly I'm moving away by switching this cost of 1 for this cost of 3. I'm paying a greater price. So you can kind of get very direct kindergarten-like intuition for why the check loss function is right with this perturbation exercise. Okay, so we just did it on the board for tau equals 0.5, and for the unconditional case, right, this perturbation exercise can convince you. You can also at home try the same perturbation exercise with a tilted loss and see that you're going to get the quantile that you want. How would you get a conditional quantile? Well, just replace this zeta with x beta. So now I'm solving for a solution that depends on x, and that is exactly, this is naively derived exactly the form of the problem that we're going to solve. So this is the general expression, and this is the check loss, so the absolute value tilted if I want not tau equals 0.5, but let's say tau equals 0.1. And I'm implementing this n estimator in beta to get the quantile regression estimate on beta. And so that we're going to see next time is a linear program, so very easy to solve even though the viscous function is not smooth. If tau is 0.5, it visualizes back the case you probably know of the median regression. So I wanted to, we're going to spend more time talking about estimation much more rigorously via linear programming, but I do wanted to show you how do we get these fitted lines tautologically this way. You can plug this in the computer and you can solve this. And this is the object we're interested in studying. Yeah. Yeah.
For the uniform probability,
Yeah.
and I'm looking for the median. So that minimizer, so anything between 2 and 3 is going to be a
Yeah. Yeah.
So that's not picking one.
No, exact. Yeah. And that's going to be true more generally because that would, when we're actually doing the derivation case, it would correspond to a full facet of the polytope. Minimizing the problem. So yeah, but with continuous data, in the regression case, you almost never get multiple solutions.
If you were to get it, the linear program, say if I didn't know about this and I just tried to
Yeah.
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 The linear program would just pick one of these things, but it probably depends on
It would tell you that you get a warning that there are maybe multiple solutions. It would pick one, and then it's actually feasible with the output of the LP to find all the solutions. A case, actually, so Yoon's a bit of an expert in that. A case of interest, the problem that Elitamer brought up, is when Y is discrete, you get now it's more partial identification. Now you get like in a fundamental sense multiple solutions, and that's kind of I think it's still open like exactly how to get the methodology right for that. So there are cases where there's structure either in the Y's or the X's that make it such that you get non-uniqueness. Yeah. In practice, it's never been a problem for me. Okay. So what have we done so far? We've introduced quantile regression. We've motivated it in part with the Gary Chamberlain example, saying, look, we want this tool to get at the big picture, to get at the full conditional distribution. And we've said at a high level, but now you would know how to plug it into the computer, how to estimate this quantile regression. Now I want to study it a little bit deeply, and I still want to proceed by analogy with OLS. And I want to talk about how this reduced form estimator, when we're misspecified, which certainly we always are, is still giving us something reasonable. And that should be a criteria you always have on your mind when you're developing or using reduced form estimators. So think about the OLS, quantile regression, maximum likelihood. Okay, so a question of utmost importance for inverse problem is when we want to interpret the solution coefficients, or at the very least the regression function, is under misspecification when we can't possibly be getting the object that we're interested in because the function we're interested in is not in the class of function we're optimizing over. Are we still getting something as close to it as possible in a reasonable sense, according to a reasonable notion of distance? So we do get that with OLS, and that's certainly a very strong motivation for relying on the method for data analysis. And we're going to see that quantile regression has the same desirable property. Okay, so let's kind of first redo OLS from scratch, but in a modern way. And then we'll repeat the exercise with quantile regression. Okay, so you open undergrad textbook or even a paper, and you get presented the model that they're studying, and they're going to present you this regression function. How do you interpret the beta? Well, it depends on the assumptions on the epsilon. And oftentimes you'll get that area x over fixed, or that conditional on the x's, the epsilon has mean 0. So conditional expectation 0. So what does that mean about? Oops, it's gender and age. What does that mean about this conditional expectation? Well, I can plug in the y. So this is being very pedantic here, but so beta naught plus g beta g plus a beta a, conditional on g and a. Sorry, that's the whole point. Well, everything is fixed except the error, and the error and this assumption has conditional expectation 0, so that's just beta naught plus g beta g plus a beta a. And so a is age, y could be, let's say, height. This could be age. So what's the problem with this expression? I mean, there's one big problem. It's not true. Right? Do you grow up linearly with age forever? It's just not true. It's just not true. But we're going to run this regression under the pretense of studying this object. So now we have existential anxiety because we're trying to estimate this object. We're gonna try to find it amongst functions of this class, and it does not have this shape. So what are we doing? You should be feel anxious now. This is the emotional point of this lecture. Okay, let's push a little bit more. So conditional expectation of height given age. Well, that's certainly not linear. Conditional expectation of income given education, same thing, you know. Elementary school, high school, master's, PhD. Maybe it's linear, maybe actually it goes a little bit faster. And when you get to PhD, sorry to tell you that. So again, it's not linear, but doesn't mean, it's not saying that this function we're after, remember we're after the conditional expectation. So it's a conditional expectation as a function of y, x's. We want to be able to change the x's, right? Change the age or the level of education, and have this function output us the conditional expectation of y. That function exists. It's just not linear in most applications. So if we keep looking, in fact, optimizing by running OLS for some solution that's linear, we're not getting what we're after. So what are we getting? We better know if we want to be serious about data analysis, otherwise we just don't know what we're doing. Okay, so let's think about the objects that are floating in here and get a sense of what we want, what we get, and is what we're getting close to what we want. So there's the regression function. That's the gold standard. That's what we want, right? We want the conditional expectation of y given x. This is very easy. It has a very tautological extremal characterization. It's just whatever function y tilde of x that minimizes the least square problem in population. And so it turns out that the function y tilde that's going to make this expectation of square difference as small as possible is the conditional expectation of y given x. So that's a very nice extremal characterization of what we want, and also we get our sample problem in the limit, so in population, but over an unrestricted class of functions. So we want that. what are we doing? Well, we're running a linear projection in population. So what we're doing, what we're estimating, if you will, is OLS. So that's going to be, take the x. So these are matrices, right? X transpose x inverse x transpose y, and that's going to give me my y hat, and of course this is my beta hat, and so x beta hat is y hat. Okay, so that's what I'm estimating, and what am I getting? What does this go to in the limit, right? This beta hat, we know it stabilizes, so it's going into to probability to something. What is it going to? Well, unsurprisingly, it's going to the limit problem, which is the population problem, but where you restrict yourself to minimizing over function y tilde of x that are linear. And so I could rewrite this. So the standard notation is y star, expectation star yx, so that's Gary's notation. And this is our min, and I can put the beta directly here. Expectation in population y minus x beta square, like that. And I can write that directly as a linear function, and that's fine. Okay, so we're estimating this, we're getting this. Are we happy with that? Right? What do we want? We want the thing we're getting in the limit to be close to the thing we're hoping to study. Is it? If it's not, then we should change jobs, right? Because we're just doing silly things. Okay, so it is in kind of exactly the sense you were hoping for. So the conditional expectation, which is what you want, if you try to get it as close as possible to a linear function, what are you going to pick up? The linear function that's the closest in this L2 sense to the conditional expectation is the best linear predictor. So this is minimized at beta star. So even though we could not possibly get the conditional expectation if it's not linear, amongst linear functions, we're getting the linear function that's the closest in a very satisfying sense to the conditional expectation. This is why it makes sense to do OLS, even though the conditional expectation, the object of study, is never linear. So extremely desirable property. We have it also for, in general, for maximum likelihood with respect to the Kullback-Leibler distance. Another reason why it's reasonable to do maximum likelihood, even though the distributions are never correctly specified. And now we're going to want to ask if we get something like that for quantile regression, especially since we're really proposing it as a reduced form estimator. Okay, so the kind of table I was sketching here is here. So I just want these two slides to be well digested. So is everybody clear about the notation here? The statement, the content of the statement? Okay, all good? Okay, and here, so this is the kind of picture, the picture time take home slide. So the best predictor for conditional expectation, we're trying to get it. That's the gold standard. We're doing OLS, so getting our orthogonal projection. What does that converge to? To the solution of the limiting problem, so the best linear predictor. Is this good? Well, yes. This is, given the class of function we're optimizing over, this is really what we were hoping we would get. It's the best approximation to the object of study. Yeah.
What is the thing that is desirable, like this kind of interpretation? Because if we think in application at the end,
Yeah.
it's misspecified.
Yeah. Yeah, so best does not mean good. Yeah. That's for sure. So then you can play a lot of games. So when I teach this to the master students, I kind of have a nonlinear function with coefficients you're interested in, and then when you fit the best linear approximation, you get the coefficients that flip signs, and so you can go completely crazy. But the idea is that you need to think. I'm an applied researcher. I did my best to model this conditional expectation linearly. I'm close, but it's not in the set. So it's a bit I'm close, but I'm not in the set. The set is here. Is there a sense in which the picture you want to have, which is I'm going to solve here, is correct? Or if you're not in the set, then you're going to get like this. So you want to be rewarded for your modeling efforts, even though the function of interest is not in the set. That would be the way of pitching it. But no, but we can talk more if you're unconvinced, because I feel very strongly about this as a good property. Okay, great. Okay, we're doing very good on time. All right, so then it's equally important, especially since I'm trying to pitch to you that you should use quantile regression on par with OLS, to ask the same question. Are we getting something reasonable or complete garbage when we run linear quantile regression, given that the quantile regression function itself is certainly not linear? If the average age is not linear in X, the 10th percentile, the 90th percentile of age, of height, is certainly not linear in H. So the same pieces are showing up, right? We have our fitted values, our conditional fitted quantiles in this way. And we have population estimates. Right? We can solve for the quantile regression function in population. Trivially, this is what we're consistently estimating, whatever solves the linear quantile regression problem in population, right? Because in sample, this is the sample average, it's close to the expectation, and since things are smooth enough, the minimums also converge. So we want to know if the thing we're consistently estimating is a reasonable object. So of course, the fact that we're consistent for whatever solves the problem in population does not tell us that the linear quantile regression estimate minimizes, we know that this tells us that the linear quantile regression estimate minimizes prediction loss according to the check function, but that's not satisfying, right? We want to study the quantile regression function, so we want our linear approximation to the quantile regression function to be close to it in a reasonable sense. So what we want is not to know that we're doing good at the forecasting exercise, so to speak, but that we're doing good at the scientific exercise, that we're getting the quantile regression function. And so, are we getting that the thing we're estimating is close in a satisfying sense? So this is what we have. This is what we want. It's close in the satisfying sense, so some norm, to the thing we want. And well, one really satisfying answer would be to put a 2 here and to say that, and have this as an expectation. So what would be really satisfying would be to get the same notion of proximity as for RLS, right? If we could get that in the limit, our linear quantile regression function was as close as possible to the true quantile regression function, that would be great. That would be exactly the same property as OLS. So we're not getting that. If we were die-hard on getting that, how could we? Well, we could sort of bake it in. We could, if you could get the non-parametric quantile regression estimator, so that's your proposed estimator, and say, well, actually, I would like a linear representation, then you could, in the first step, estimate non-parametrically your quantile regression function, maybe by binning the x's, and then just find, according to an L2 norm, the linear function of x that's the closest to this non-parametric estimator. And so what's going to happen here, this converges to the true quantile regression function, and you're going to get, in an L2 sense, the closest linear approximation. Then you bake in the L2 approximation, so that's very nice property of minimum distance estimators. That's nice. So in fact, the numbers I showed you before, the unionization example, that's how it was computed. So it's not unreasonable. And certainly a motivation was to get this best approximation. Yeah. Okay, so why don't we do that in practice all the time? I mean, there's something here you don't want to have to do. Yeah. Yeah, exactly. Right. There's the whole point is to get like a just from estimator and LP, put the x's, the y's, get the beta hat be done. This requires being able to run an unparametric quantile regression, which is not a walk in the park. Okay. So what we're interested in is not the best approximation properties of the new estimators, the best approximation properties of the quantile regression function. So the beta that minimizes the check loss. That's the estimator that's used all over the place. That's the estimator we're going to use, so we want to know that it's reasonable. So we're interested in the properties of the linear quantile regression estimator, this linear program. That has been worked out fairly late when you think about it, by Josh Angrist, Victor Chernyshkov, and Ivan Fernandez-Val, and they get the best approximation result. So they're gonna tell us essentially in what sense, if any, we're minimizing the distance between what we want and what we have. And then the paper does a lot after that. Since it casts you in the Euclidean space, you get a notion of orthogonality, you get residual regression, you can talk about OVB. So at least conceptually, it's very nice. And they also do, they also get a sandwich formula for the asymptotic, it's already a sandwich, but they get large sample inference that's robust to misspecification. Okay, so this is the result. So we're getting almost what we want. So we're getting that what we're going to in the limit, right? You can put a star here if you want. We're getting that what we have in the limit is going to be, we want this difference to be small, is going to be close to the true quantile regression function according to squared error, but a weighted squared error. So it's weighted L2 loss. I would say that's a perfect news. That's good news, right? These weights are not too crazy. We're closing not quite L2 cents, weighted L2 cents. But what I want to know is not the fine details of the distance between my model and the true quantile regression function. I just want to know that in some reasonable sense, I'm as close as possible. Some reasonable version of distance. So on first order, I think this is very good news. Right, we can put it in notation that's even more encouraging. So if I look amongst, what I'm getting in the limit is x beta star, as I was saying here. And that is the function, if I'm restricting myself to linear function, that's going to be as close as possible to the object of interest, according to some norm. Well, a norm that's a little bit weird because I'm getting weights. But one way to reassure yourself is that these weights don't fluctuate like crazy, so this is a reasonable norm. We could even expect those weights to some extent. And so we have anxiety, now we really fit the anxiety. We're getting that what we're estimating in the limit, what we're getting in the limit, the linear quantile regression function, is as close as possible to the object of study, the true quantile regression function, in a reasonable sense. So that's the take-home message. Yeah. Yeah, I'm gonna, because I try to not critique them right away because I want to emphasize that the message is positive, but the next slide is going to is going to be longer on the weights. Okay, but so yeah, I'll say more about the weights in in a second, but I want to, you know, if this was master's class, I stop here because I really want to press upon the point that this is good news. But since we're between aficionados, we'll critique the waves a little bit. But first, I really want to let it sink in that like we are getting a best approximation result to the quantile regression function, and this is kind of extremely reassuring for practice. All good? Yeah.
Just say, suppose that I start just in a more naive way. I just really take the analog problem with the correlates the best linear prediction problem, and I really say, well, in the population, what would be the data such that the expected value between the quantile function for a particular tau and x prime beta and all that squared, what is the data that minimizes that? Do we know what's the answer to that? Like, if I just try to solve that problem one way.
Oh, no. You want to like solve that problem so that you can look at it.
No, I just want to solve the problem and then look at the sample analog.
Yeah, yeah,
It's not going to be quantum regression, but
yeah.
that seems like something I could be interested in.
So you want to write this problem in population and then do clever math and get a.
Go to the other side. If you go to the other side, yeah. So the other, yeah. So what I want to do is I want to kill the weights in the first display.
Yeah.
Omega tau.
Yeah, yeah.
Let's write that problem.
Yeah.
Nice q tau y of x.
Yeah.
X prime beta.
Yeah.
And I'm going to call these, quasi quantum regression.
Yeah, yeah,
And then just look at the sample analog.
yeah. So the naive sample analog is the tautological sample analog is that. Can you start from the population problem with this, do clever math, and get an expression for beta that has a sample analog? That would be amazing, but I don't know. Yeah.
Is it also that maybe, for the x's that you never see, you don't care about the loss that you would incur?
Yeah.
So it makes sense to have some weights. I don't know about those ones.
Yes, that would be, but that's not what these weights are doing. Okay, so this is let's go to the weight. So this is the good news. We're reassured. We're doing the best we can within the class of linear models with respect to a notion of distance that is not too crazy. Now, if we want to go sort of second order of precision, want to complain a little bit, well, let's think about those weights. So what the authors propose is to take they work out an approximation of the weights, and they say the weights are bigger where the quantile regression. Let me just read it out to get this open. So you want more weight at x's that generate y's that are more likely to be near their true conditional quantile. So in this sense. But that's telling us that there's some approximate probabilistic interpretation. It's not clear that it's a favorable one, but that's something to read into. But then, so Blaise is not here right now, but we're talking about this paper, and he had an excellent point. So these weights, and here we're a little more critical, and I think people have thought about that stuff. So, okay, the formula, this monster formula is a little bit disgusting, so that's why the authors gave this more concise approximation. But it hides something important. This is a function of the degree of misspecification, right? It's comparing x beta star and the true quantile regression function. We're given the degree of misspecification. This is fine. These weights are still going to come in fairly stable, and we're going to try to be as close as possible to the true quantile regression function in some weighted L2 sense. But then if I want to do a slightly different exercise of comparing the distance between my linear approximation and the true quantile regression function for different models, I can't really do it anymore because the notion of distance changes. So in particular, I may have a model that's more specified in a kind of sense that's fixed across model and more reasonable to me. but for which the distance becomes a lot more the weighted distance becomes a lot more forgiving because the weight changes. So the fact that the distance is different for different models makes it that I can't really compare models. And in fact, it means that directly doing model selection in sample, according to this check class, is maybe not completely warranted. Right? That's very interesting. So this, nobody I think has really studied that, but there's something to do there. Maybe it doesn't make sense to pick between models by looking in sample at your check loss. Maybe you really have to cross-validate. And that's an extremely popular question in classification, so it might be interesting there might be a publication payoff to looking at that here. Okay, so so again, this is kind of, we're getting in the nitty-gritty. We're criticizing, but I'm not trying to push away the positive message. The main message is a positive one. We're very, very happy about getting our best approximation, even though we're never correctly specified. Okay, so kind of wrapping up, I just want to make some quick points about inference, because you're going to go and you're going to do inference. Oftentimes you're going to do huge large sample distribution theory. There's some little quirks, and I want to talk about interpretation a little bit more, and then we'll be able to wrap up. Okay, so there should be a hat here. So we have CLTs for the regression coefficient. We get the typical sandwich formula, inversion, inverse Hessian, variance of the score, inverse Hessian. And then we have little complications, because we can look at these objects. So the variance of the score is fine, but this Hessian, it looks like the expectation of the Gram matrix, and then the density of the errors for the y minus sigma beta, which we were talking about earlier, conditional on x. And even if you're willing to make this very strong assumption that the errors, the conditional solution of the errors is the same as the unconditional solution, which really means that your fitted lines at different quantiles are parallel, so it's kind of making quantile regression moves. So it's a very, very strong assumption. That would allow you, of course, to plot the density outside of the expectation. This assumption is used in many places. Inference seems to be robust to it, but in any case, whether the density is here or here, in some sense, you're going to have to deal with non-parametric density estimation. You're typically going to keep it as a sum n in the sample average that approximates this expectation, but there's still a notion of bandwidth that's going to come in for estimating this density. So that at a very superficial level, think of estimating the density. It's non-parametric density estimation. You need to pick a bandwidth. In fact, we're going to, we're going to be a little bit more clever about it, but we're still going to need to pick a bandwidth. So let's look at support vector regression. It's a median regression in the special case of that. And if I'm just proceeding with the Wald estimator, so doing inference on beta hat, estimating the asymptotic variance, and building your usual confidence interval that way. In building the asymptotic variance, I need to pick a tuning parameter because I need to estimate this non-parametric distribution function. And so this is a menu of a priori reasonable bandwidth values, and this is coverage under the norm. So the nominal level is 0.9, and I can get essentially any coverage between 1 and 0.25 by picking the bandwidth, which means I can give you confidence intervals of the width you want. I can cheat. So that's not good, because then we're not going to believe the output. If someone wants this estimate to look precise, just pick a different bandwidth and report very small confidence intervals. So we don't like that. But we can get this line. And that's with the standard large sample approach. So I just want to name it to you, present it to you so that you know about it. So we're not going to want to estimate beta hat directly because we don't want to deal with the asymptotic variance of beta hat because we don't know how to estimate it in a stable way. So we're going to invert a different test. How do we do that? Well, an easy way of doing that is a kind of standard recipe would be, so I'm going to invert the test. So how do I run the test? Let's say I want a confidence interval for beta 2. So suppose beta 2 is equal to beta 2 naught, that's my null hypothesis. Build the test statistic this way. So concentrate out x2 beta 2 from y. If I get the right value of beta 2, there should be very little x2 variation left in here. Regress that on x1, and that's going to produce short residuals from that regression. If indeed I took out all of the x2 variation, so this is a vector, the inner product of these errors with x2 is going to be small under the null. But if instead of taking out the correct value of beta 2, which maybe was 0 or 1, I put beta 2 1 million here, then I'm going to have a lot of x2 variation in the residuals, and so this is going to be large under the alternative. So that's a test statistic that's going to have power for the obvious reasons. I can also take the sign of this. This is still going to covary or not with the x2 depending on whether I'm under the null or not. And if I do that, I can demean and divide by the standard deviations. I can studentize. This object is going to have a very well-behaved limiting distribution. It's going to be normal 0, 1. And the variance of the unstudentized object, so the variance I need to estimate, is tractable. And in particular, under this homoscedasticity assumption, it's going to be completely pivotal with respect to the density, so I won't have to do any non-parametric density estimation to do. Even without assuming that, you see how this black line is not completely stable in the bandwidth. Even if I do not make the homoscedasticity assumptions, on the general assumptions, I'm much more robust to bandwidthization, extremely stable to bandwidthization. It just is the nice property of taking this object as the test statistic. It also turns out that this is going to correspond to the dual feasibility condition for x2, so it embeds inference very nicely in the dual linear programming structure of quantile regression. But it's really this plot that is the motivation that made this approach to a large sample inference standard for quantile regression. So this is, when you run R, this is how your confidence intervals come out, and that's why they're not symmetric, because you're not doing beta hat plus or minus, you're really inverting a test. Okay, when you estimate your beta hat tau at multiple taus, you often want to present it beta hat tau versus tau when you want to make comparisons across tau, across quantile, and see that they're significantly different. Typically, you want bands. I've been talked about jointly valid inference, so bands that are valid uniformly, not just pointwise. So these are easy to get. The theory is complete for that. The last point I wanted to make, and this is kind of a very simple point, but people make the mistake so often that it's worth specifying. So when you talk about, suppose you believe you have a causal effect because you have a randomly assigned treatment, and you have before treatment and after treatment, and have x beta 0.1 and x beta 0.9. And what are we saying here? We're saying that, so this is the 10th percentile. We're saying that after treatment, the 10th percentile move from this level to this level, and so people, the state of the distribution has improved in its outcomes on measure of health by some. So it does not mean that the person on the 10th percentile improved by this much. Even if we have panel, this guy could be here now. It's really about the quantile of the distribution, not who is on that quantile. The people, even if it's a panel, could reshuffle over time. What we're picking out is really something about the shape of the distribution, the conditional heteroscedasticity, and that's important to keep in mind. I think just when verbally people make that mistake quite a bit. Okay, so wrapping up. So the quantile regression reveals aspects of the conditional distribution that OLS misses. I like the unionization example, extremely compelling in that dimension. User-friendly inference obtained. So for large sample inference, this is called regression rank score inference. So you get very, very stable large sample inference. Confidence intervals are not necessarily symmetric, but I think we can emotionally get over that. You can bootstrap. You can bootstrap the quantile regression, so that's available too. So you're going to solve an LP, 1,000 times. That's fine. That still will be very fast. Interpretation at large may be a bit challenging. So this is kind of, I think somehow there seems to be a little bit of an hesitation when thinking about the effect on the quantile as opposed to the effect on the mean, the average effect. I think it's not fundamentally more complicated. I just think people feel more comfortable, like non-technical people maybe feel more comfortable talking about the average effect without understanding what it means than they are about talking about the effect on the quantile, which is also maybe that lay people maybe don't know what the quantile is. But that might just mean that there's some work to do into like visual representation or how to articulate findings about the quantile when you're writing a newspaper article for lay people. But so there might be a bit of a communication challenge, but certainly in anything near academic research, that's not a problem. That's not an obstacle. I think the only obstacle is ourselves. We just need to run the quantile regression. The software is there. Any serious supply people knows how to interpret it. We just kind of, I think as a community, need to make a bit of a push. Yeah, okay, so that's it. So I hope I've convinced you that you can access more information by running the quantile regression at different quantiles as opposed to just the OLS. And so this kind of, today was a bit of an applied pitch, a pitch for applying quantile regression. Tomorrow we'll go deeper into the machinery. I think in terms of regression analysts, there's really a desire to understand the closed form-ish expression for beta hat. It's so satisfying in OLS, right? This orthogonal projection story. Can we get something there? And then we're going to see something fascinating. The same way linear algebra reveals the structure of the OLS problem, linear programming, the duality of linear programming, in particular linear program duality, is going to reveal and shed light on the structure of quantile regression, and in particular the closed form for the beta hat. So that's going to be the game plan for tomorrow. If you get a chance to skim the proof in your notes for the closed form for beta hat, that might make the lecture tomorrow easier. Yeah.
So everything was fine until you did the example.
Yeah.
So if, like you say that, this person is allowed to start from the low quantile in the initial distribution, after and jump to a high quantile in the final distribution. So this means that the other ways it can happen too. So you have in the initial quantile, in the initial distribution, the people in the high quantile, and you can drop. So if we assume, let's assume first that it's rank preserving. So before and after. So if it's rank preserving, like treatment in each quintile is positive.
Yeah.
But if it's not rank preserving, this means that you have both negative and positive.
Yeah.
So how can you distinguish from?
You can't, right? This is if you add rank invariance, then this guy moves here, and
But in reality, like the sudden case where you don't have rank preservation, you have a much larger heterogeneity in the effect of the treatment.
Yeah. But so there are two parts. So if you're interested in that, like were there positive effect, negative effect, then you can go to the distribution of the treatment effect, and so that would be so Freshev-Ding bounds, for instance, on this distribution function of the treatment effect. And so we have like two experts here of that problem. So Amkar, if you want to know how to compute that, Amkar can tell you. Okay, so that's one answer. Now, should you be interested in that? I want to help people who are worse off. I don't care who is worse off. I want to help I want to make the bottom of the distribution better. So for policy purposes, I don't need this rank invariance assumption.
Okay, so basically, it's not describing the distribution of treatment effect, which is something that could be completely different from what's.
So it's the treatment effect on the quantile. But my point is that I think sometimes there's a reflex of thinking that is this qualifying because you don't know what happens to the person on the quantile. I don't really care. I'm a policymaker. Whoever is the poor person, I want to make sure they're richer.
Okay.
Yeah. That's it. Okay, thanks. Yeah, any other? Yeah.
So when you were talking about the regression rank score, you gave us the sort of intuitive picture.
Yeah.
The epsilon hat times the x.
Yeah, so I cheated a little bit. Right? So I took the sign of the epsilon hat, but really is the variables that are going to come out of the dual, all but, let's say there are p regressors, all but p of them are going to have this form. Yeah.
I wanted to ask, that step going from the epsilon times x to the sign of epsilon times
Yeah.
x, I'm sure we'll talk about it tomorrow when we learn about feasibility and things
Yeah.
like that, but without knowing anything about linear programming, is
Yeah.
there any intuition for why we would design a test statistic that uses the sign?
Yeah.
as opposed to-
So I guess there's a two-part answer. Like either you're like living inside the matrix and you can see like 20 steps ahead, and you knew that this would give you a nice asymptotic variance expression that you could estimate well. Other than that, you could think that, oh, if I take signs here, this becomes 0, 1, then this is going to look like a rank test. And then you can have hope that at least for nulls on the full vector, this procedure is going to have exact validity properties. We're going to touch upon that in the third and fourth lecture. But other than that, no, this is not only the dual feasibility condition, this is essentially rewriting the objective function. So you're using the first order condition. You're testing the first order condition, which is a very naive way to build a test statistic. Because the objective function for L square, for OLS is error square. So first order condition is linear in X. Now our objective function is L1, and so one derivative below, instead of having as for OLS an orthogonality condition of this kind, since you differentiated something that was linear, you're getting an indicator. You're getting an indicator on the error, basically, on the sign of the error. So there are many ways to get directly at this by thinking about what you want to test. In terms of anticipating a good test, it's kind of, I mean, historically they came up with this for the reason I said, like it's the first order condition, it's your dual feasibility condition, and it looks like a rank test. Historically, the reason why it stayed is because the asymptotic variance is much easier to estimate. So it was not anticipated. So it's a good question. The reason it stayed was not the motivating reason. Yeah. Okay. Any other question? Yeah.
So I was trying to understand the relation between that Ingres Churchill paper and the one you proposed in the beginning where there's a check function, the objective function.
Yeah.
Since check function doesn't really show up in their objective function.
No. Sorry. Yeah.
Does that mean we?
If I want to minimize the L2 distance between my regression function and the true contradiction function, I can do minimum distance this way. So this is saying if you want to minimize L2 distance, this is an estimator you can use, and we don't really want to use estimator because it requires non-parametric density estimation. Okay, now let's go the other way. Given that I am using quantile regression, this, minimizing the check loss, what am I getting? So Angus, Chernuskov, and Esval, they start by saying, I'm running quantile regression, minimizing the check loss. What am I getting? And we're getting this. So you're not seeing the check loss in their characterization, but they are starting from the check loss. If I minimize the check loss, what do I get? I get in the limit But we didn't know before what we were getting. They worked it out, and this is what it looks like.
It's important that we incorporate this weight.
It's what?
Is it important that we incorporate this weight calculation?
We don't have a choice. When you run quantile regression, this is what you're getting.
So does that mean in practice we're also calculating this weight?
No. No. In practice, you're minimizing. So in practice, you're minimizing this, but this is the distance between the data and x beta. And that's going to tell me also that in the limit, 1 over n here, this is going to become an expectation, and I'm going to minimize in the population the distance between the y outcomes and my x beta expression today. Because I'm doing good at forecasting. But I want to know if I'm getting close to the conditional expectation. So they're saying, whatever this converges to, can I write it as minimizing some difference with the true quantile regression function? And it's that. And again, it's not something you choose. It is what this is minimizing. Yeah.
Regarding the point of the misclassification, you mentioned like the weights here depend on like a certain type of model, like a certain degree of specification
Yeah.
is needed for model selection. So I wonder if there's like other estimators where we can do more robust degrees of misclassification. Is that a valid question?
Yeah, that's a good question. So I mean that's my kind of homework assignment here. I mean I think it's worth thinking about, yeah, because we wouldn't have that issue if we did the minimum distance, because by design we're minimizing unweighted L2. Okay, so that's one estimator I know. The other estimator I know is quantile regression, and then we're getting this issue. So yes, there's motivation for pushing farther exactly your question. I don't know. I don't think we know how to do that. Yeah. But somehow, then you need to think about the deliverable, because somehow you're not gonna make everybody switch from quantile regression to something else because of this, admittedly like third order point. But it's still important. So is there something we can? Is there a point to make, or is there a clarification to make about those weights? The solution is easy, right? If you're comparing models, you can cross validate according to whatever notion of error you want. But maybe even just formalizing that would be interesting. Yeah.
So in practice, I got a wrong one of these things.
Yeah.
You open it, so my apologies. But so you just set up a grid of values of tau? Is that how it works?
Yeah.
Set up a grid of values of tau and
Yeah.
then do the linear programming for
Yeah.
these values of tau?
Yeah, exact. So there's there's a paper, like very, very like nerdy paper about computing the number of different values that beta hat can take. So even if you wanted all the values, there's only finitely many.
Yeah, because I was going to ask you about that. With these things somehow,
Yeah.
you should have some interpolation.
Yeah.
Because the data is
Yeah.
different, right?
Yeah, exact.
So but there's a paper about that.
There's a paper that goes through the exercise of like saying, I mean, in the linear programming structure, it's clear where you switch. He has a fairly old paper. I think it sits on that too, but he gets the number of different beta hat values that you could get. Yeah.
And so it just, is there any restrictions on the shapes of the data that you can get, or
Yeah.
anything goes?
So it's very easy to add the non-crossing restriction. That's a linear condition. So you stay in an LP, and you just add this condition, and then you basically let's say you have 20 taus, you solve for the 20 taus at the same time. If you don't have non-crossing condition, you're just solving 20 LP separately. If you have non-crossing conditions, then it becomes one bigger LP, but it still runs fast.
For the standard implementation, you don't have that condition, right? You're solving for these things separately.
Yeah. So I don't know for R packages and side packages if you have the non-crossing condition, but I would suspect there's an R package, and it's pretty fast to write down, like you're like in Gurubi. So So I mean, so Abla is gonna be here, so he also knows a lot about, and actually Alfred, but he's not here this year, about like resorting, like reordering the quantiles ex post. So I don't know a lot about that, but that's the properties of that are known, and basically it's fine to do it. Is the message? Yeah.
And then lastly, the only thing is do you know if anyone has done this fully Bayesian? Like, you start with the
Yeah.
model that you described, Q of U, Y,
Yeah.
X, and you put a prior on
Yeah.
those things, and then you just
Yeah.
do probably something fancy because
Yeah. I think this is where so maybe Pierre knows, this is where the Laplace distribution I think comes up. So yes, there's there. I forget, but I know they've I know that for some reason it connects with the tilted exponential literature. So it was hot for a little bit, but yeah, I can find the references, but I don't remember. Yeah. Yeah.
So this is a question that was brought up a few times of what if we wanted to take the minimum distance estimator more seriously? What can we learn about it? I'm wondering, these weights show up in so we have this, we're trying to minimize the expected check loss in the population, and we showed that it can be written in a way that tells you that y minus x prime beta, you're trying to minimize the norm of that, some norm of it. And I'm trying to think about, in the OLS case, why is it the case that there's a degree of misspecification in the same way in quantile regression? And if I remember correctly, the reason why the best linear approximation and the best linear predictor happen to be the same is that they only differ by a constant in their objective, and that constant doesn't matter, and so
Yeah.
the OLS, sorry, the solution to the best linear approximation problem is the same as the solution to
The proof you're saying the proof for minimizing this to minimizing is very short.
right.
Basically. Yeah.
Right, and it comes from the difference between y and expectation
Yeah.
of y given x.
Yeah.
And I'm trying to think if there's something, if that proof strategy can be used to better understand the minimum distance estimator and think about how y might differ from the quantile function of y given x.
Oh, but in the minimum distance, it's even more trivial because you're starting from here, and you want to get here.
So then, does that mean that whatever solves the minimum distance problem is also going to be the one that solves
This. Yes, because the minimum distance problem is using the simple analog of this objective as its objective. You're minimizing in beta, but instead of having the conditional expectation, you have something that converges to the conditional expectation.
Sorry, I'm trying to draw a parallel between the first line and the second line.
Right.
For
So
OLS,
what are you calling the minimum distance?
Sorry?
What are you calling the minimum distance estimator then?
Instead of expectation of y given x, you have quantile function of y given x.
Yeah.
And I want to compare that with expectation of y minus x beta and understand, like, why is it the case that these weights show up here but not in
Oh yeah. Okay, so there's no minimum. So minimum distance, I mean like the estimator where you're trying to minimize in simple the distance between x beta and some non-parametric estimate. So we're not talking about that. We're talking about why is it that when we're starting from here, and we're trying to get to somewhere like here, we're not getting to that, but to the
So I think that's one way to phrase my problem. But
Yeah.
I think there's other contrasts we can make. So here using the check loss, and then you're comparing that to that weighted L2 norm. But I think you could also think about the unweighted L2 norm between the quantile function and x beta.
Yeah. Because the difference is I can minimize this. I get the limiting object of quantile regression. I minimize this. I get the best linear predictor. After that, yeah, I think there's just I'm not sure what kind of interesting comparisons would come up. Yeah, we can talk about it more. But yeah, so the point just for so that everybody's on board is that argmin beta of this is equal to argmin beta of this, and separately argmin beta of this is equal to the argmin beta of this. And yeah, I'm not sure. Yeah, I'm not sure. We could look into how looking at the difference between these two. But the proof for this is not super long either. So I think that then you know everything there is to know once you have the path from this to this, the path from this to this, and compare. Yeah. Okay. And last question. All right. Okay. We're just right on time. Perfect. Thank you so much for your attention, and then I'll see you later. Yeah. Thank you. Yeah. Huh? Yeah.
So I'm thinking we might be interested in an object like this. And I'm trying to say, like, this is parallel to this, and this is parallel to that.
Yeah.
Each of these objects have something here where it's in terms of y, and I don't have to do this non-parametric estimation with the expectation function and the initial quantile function. And I'm wondering
You want, yeah.
if there's something
Yeah.
that can go from here to here.
Yeah.
And I was thinking, how do we get that in the OLS
Yeah,
problem? We are able to add and subtract y.
Yeah. Oh, you're saying I know the proof from here to here. I can read it backwards, going from here to here.
Exactly.
What happens if I try to go backwards from this to something? So the hope is that by the time I get a y here, the rest is a constant multiplicator, additive constant, or something like that. And then to Pepe's point, well, if it's that, then, well, no, so that wouldn't work, right?
Right.
We know that we're not gonna get argmin.
Right.
But could we get argmin? Maybe I need to write it. Argmin e some function y minus x beta. So that's Pepe's question.
And perhaps like what we discover is this. It's exactly this function. But
No,
I'm
no.
wondering if there's.
No, it won't be because
Right.
we would have the weight. Yeah.
Yes. Right.
So one worry is that these guys are going to show up here.
Okay.
So some version of that. Because if you pick it up going this way, maybe when you go this way and they're not here, like they kind of what would have canceled them shows up. Yeah. So I would say like yes, very high payoff if there's a tractable G. I am skeptical. That there would be, yeah.
One part of the proof going from.
But I mean, staring at the proof for this is a good exercise anyway. And then after that, you'll have all the tools and ideas to try this.
Okay.
And if you can figure it out in one sitting, then move on.
Okay. One part of the proof here has to do with the orthogonality condition, expectation of
Yeah.
x times. And we don't have orthogonality showing up here in the same way. And
Only when these are there. Yeah.
so I guess this is like a two-part follow-up. One is, well, actually, I'll just ask one for now. The orthogonality conditions here came from taking the first-order condition of a problem that looks like this, and first-order condition looks like last year. I'm wondering if I were to take the first-order condition for this problem and the first-order condition for this problem, what might we be able to learn from both of them, and whether or not like the orthogonality condition here was expectation of x times residuals equals 0. Do we have expectation of x times, as you pointed out, sine of the residuals?
Yeah, exactly.
How would it's comparing the FOCs, because they would be equivalent, I think, how might that
Yeah.
help us, if it will?
It's going to be tough because the inner product you want to kill shows up in the same norm here,
Right.
but not here. So I don't think you're gonna have payoff thinking about one as the operator and the other. Like I was just thinking like do you in a functional analysis kind of sense get to generalize the inner product but not really.
Okay.
I don't see it. Yeah.
Okay.
I mean, yeah, I think it's a good question. I think like, I really think spending like a good long sitting in the proof of this is high payoff. Especially now that you have a problem in mind, it's even more like satisfying, I think, to like read the proof. I think you might convince, I don't know, you might not convince yourself you can't do anything like that, but if there's any direction, it would be really great.
Right.
Yeah. Yeah.
And to learn about proof of this, that's just checking out the paper.
Yeah, and also they have they have a longer working paper that has more details.
Okay.
I've only worked with the published version, but the longer with the other, yeah, probably you'll see it like it's just longer, and it's fine online. Yeah. Cool.
Thanks, Guillaume.
Yeah. 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 How are you?
I'm doing well. I had a question on this like second optimization problem. I thought there was something like kind of subtle there that I may have been missing.
Okay.
So
I'd love to know.
can I write on the?
Yeah, but yeah.
Sure.
Yeah, we're kind of low on charts.
Yeah. So
Exactly.
is it that like beta star is the arg min arg
Yeah, I don't know.
min of this?
Yeah, it shows up here. Yeah, exactly.
So it's like a fixed point problem.
Yeah,
Right.
yeah. So so the less subtle part is right. So you solve it once with where beta shows up in here and in here. It gives you beta star. If you plug beta star and you solve it again, you get again beta star.
So beta star also solves this.
Yes.
Okay, so it solves both problems.
Yes. Yeah.
Okay.
In fact, you kind of get this first, and you're like, well, okay, this is not weighted L2. They're like, well, if you plug the beta star back here, you still solve for beta star. So in that sense, it's weighted L2.
Okay. So then what's the point about like this, I don't know, the second to last bullet point, right? So like,
Yeah.
compare distances for different degrees of specification.
Yeah.
Right, because this weighted, these weights don't depend on beta star, right? So it's kind of a universal.
They depend on beta star.
Well, but they can depend on beta star, they cannot depend on beta star, right? So like there's
So
a version of this problem.
if I'm comparing two different models,
Right.
the beta star is different.
Wait, so what do you mean by two different models?
I want to regress height on age and gender, or height on age square and gender. And now these weights,
I see.
it's going to depend on a different x beta star.
Okay.
And so they're different. And so the notion of distance that this becomes after fixing the beta star here is different because the weights are different.
Sure. So the model, as when you say model as in, you mean model as in like what's in X?
Yeah,
Okay.
exactly. Yeah.
Not the functional form of.
No, the true x beta star that you get in the limit because you change x, so it's different.
Right.
But you see how it's kind of not. We don't like this. The point. You see the point here.
Yeah, I mean,
It's not a great property.
yes. I see the third point because it's hard for me to wrap my head around, but I'll give it a little bit more thought.
Yeah. Cool. Yeah. Have you talk more? Yeah. How are you? Good to see you. Yeah. Yeah.
Kind of jumping on is there a reasonable solution, or like is there a way to approach like standardizing the distances in this setup? Because
To tackle the second arrow.
I otherwise it kind of feels like almost circular in nature,
Yeah.
right? Like,
Yeah. No. So that's where we're at. Yeah. Like yeah. That's why there's the third arrow. Like this kind of we had nothing. Now we have this, and we're very happy to have that. A critique is this, and that's where we're at. Yeah.
it's not that the critique like fundamentally undermines the value of the.
No, by we. But yes, we still have the first arrow. So given that I'm gonna use this model, which beta am I gonna get for this model? The best beta in a satisfying sense. So that's comparing betas for one model. If I start to compare between models, now I don't have a good notion of distance. Now we can go and practice and check. The notion of distance might change slower than the model, and then it's fine. But that would also be nice to try to learn.
Would there be a way to like use a different like comparisons? I don't know, maybe.
Yeah. You can go out of sample.
Okay.
Yeah. But your out of sample is the forecasting exercise. It's not quite the distance between the relation functions. Yeah. Okay. Cool. Interesting. Yeah. Hey, salut, ça va? Yeah.
Merci pour l'opportunité.
Ah, bah oui, ça fait plaisir.
Deux choses en français.
Ouais.
en anglais, là. Donc, c'est ça, avec la réponse que tu m'as donnée, je me demandais, au final, l'exemple sur les syndicats, comment ça work out, là, parce que je me disais, OK, si c'est pas un preserving, finalement, tu dis, OK, dans le fond, les gens à faible salaire peuvent finir avec très haut salaire, puis les syndicats, les gens avec très haut salaire peuvent finir. Ça fait que tu aurais une plus grande compression de l'échelle salariale. Mais là, mais je pense qu'au final, c'est vraiment juste mieux de regarder la distribution de l'effet de traitement. Et quand même, si un naive quantile regression n'est pas rank preserving, c'est quoi vraiment l'information que ça donne pour ce genre de cas-là?
No, I think I still care about fundamentally care about the effect on the quantile.
Okay.
It doesn't matter to me who's on the quantile. Now, in the unionization example, I think in practice you'd be tempted to argue that people are not flipping ranks like crazy.
Yeah, sure, but it might still be the case that, because unions kind of compress the distribution, so it might be the case that the compression at when you're initially at the high end of the distribution, it can be misleading if you have a non-significant effect, but finally, because you have some switch in ranks, you go down.
Yeah.
Just a small
No, that's possible, but
that's why you
that would be more information. But
but that's why, according to me, it's just more important to look at the quintile of the distribution effect itself.
But then that won't tell you who's getting what's the quantile of the person getting which effect either. So that's not gonna solve your problem.
You won't get the quintile of who.
You're gonna get the distribution of the treatment effects. You might see some negative effects, but you don't know who's getting those.
Yeah, you might. Yeah, like if you look at conditional on what you observe, you just in the basic definitive setup, you can still associate the quantile.
Oh, but you have panel,
Yeah,
but,
in this case.
But I'm saying if you have the distribution of treatment effect.
Yeah. Okay, I see. No. You're right. You're right. But usually in panel, you have your.
But if, in panel, I see how the ranks change, so I don't worry about that either.
Okay.
So, but I think really the point is there's a case to be made for the effect on the quantile as the object of interest. It's not I wish I had the effect on the person of the quantile, but I don't see that. I actually don't even care so much about that.
Okay.
And in fact, I tell this story to see people could change rank, but as we just said, you're not using this on panel, you're using this on cross section.
Okay, that was a missing part. And the other thing is just that you didn't talk much about the conditions. So in order to get the best predictor, the best quantile predictor, So all the conditions kind of similar to what is required in OLS in terms like endogeneity, but exogenous, exogenous stuff.
Yeah,
Are there any other like specific conditions that in order to get to the result, like to this result of the weighted L2 norms?
Oh yeah, so there's one big thing that I didn't talk about is in OLS, if you get in addition to if you get measurement error on the classical measurement error on the left-hand side variable, you're still going to get
on the left-hand side.
Left-hand side.
If it's ID,
yeah,
right,
it doesn't change
issue,
it doesn't change the conditional expectation, and I think you're still getting the best linear predictor, no problem. In quantile regression, measurement error on the left-hand side variable is a shit show. You
I see totally.
Dilution to the median. Towards the median.
Okay, reversion to the
median.
To the median. Okay,
with symmetric errors.
Unless the errors are correlated with your quantile, but still no. You need strong assumption in order to make it not.
Yeah.
It's a stronger assumption than.
But just generally speaking, like measurement error on the left-hand side variable.
Okay. Well, that's a good point to know.
Yeah, and it's a tough problem because you would think since it's basically errors on the left-hand side variable, you just don't want to overfit to them. We should know how to do that, but we know. Okay, so what do we know? We know if the true quantile regression function is linear, then you're identified even if there's left-hand side measurement error of unknown distribution. Okay. But we just spent an hour and a half saying we're never well specified as linear. So what happens then? And nobody knows. Yeah. The best we can hope for is that you're getting a result like this with a different norm for some estimator. That there is an estimator that's going to give you something like this with a different norm. That kind of like. So let's say like you have like you're not well specified as linear with a quantile regression function. So you don't want to adapt too much to noise. Okay, that sounds like I want like a penalized estimator, maybe something like a lasso or blah blah. And okay, if I run this lasso, that makes me not overfit the noise too much, the measurement error on the one. What do I get in the limit? Well, not this, because now I'm running something different, but I get something like this, and we don't know. And you might not. You might. Actually, we don't know that if we're identified for some sort of best linear predictor with left-hand side measurement error when you're misspecified as linear. That's okay.
When they're misspecified.
Okay. So that's like super important. And no, we don't know. We don't know the answer to that.
Okay. I don't know. I really don't know much about the quantile regression literature, and maybe, as you say, it's super important. But I'm gonna definitely look at.
Well, I mean, so you know. Last left-hand side measurement error paper that was not completely ridiculous was the econometric cost. So okay, we take that as we're interested in. And then the real case is misspecified as linear. So it is.
Okay.
We definitely want the two together.
Sure. But as you mentioned, so reversion to the median is a well-known case in.
For symmetric errors, it's very it's easy to see.
Good. I'm gonna look at that.
Yeah. Cool. Hey, how are you? Yeah, good to see you in person,
I was sorry. So this is my first time learning about quantile regression. So I lost you a bit earlier. So when you say the loss function, right? You mentioned that it was like tilted with respect to the quantile you're interested in. Like, can you explain the intuition about that?
Yeah. So that's for the median. And that's going to give me this point as the median between 1, 2, 3, 4. And let's say now I want not the median, but the 40th percentile. So I'm going to tilt the loss this way. So positive errors are going to pay a smaller price than negative errors. So I'm going to make 1 negative error and 3 positive errors, and that's going to minimize this cost.
No, because it's
Because
not supposed to be in the center anyways, right? Is that-
no, exactly. No, I want this point of this set. That's the 30th percentile. And okay, we can do the same perturbation exercise here. If I move this here, I don't pay this price anymore, but I pay a price here, which is higher than this. So that's not good. And if I move here, then I don't pay this price, but I pay a very high price here. So I minimize the objective, I minimize the cost here. The fact that this is cheaper as an error than here, it pushes the the minimum to the left. Yeah. So the perturbation exercise is kind of very instructive.
Oh,
Yeah.
and then and this is equivalent to having like a weight and then this Q, right? Like, like do we show that it's equivalent?
No. This is the paper.
Oh, this is
And the proof. I mean, the proof is you could read the proof. It's not too hard, but in class it'll take half an hour. It's still like when it's one page.
Gotcha. Yeah, but like the weight is just given in that form, right?
Just that pops out like that. Yeah.
Okay,
Yeah.
So I'm not supposed to like understand.
No. Even they like this approximation, they work it out in the paper because they're like, well, this looks like crazy madness, so this is close enough to it, and this we can read. But yeah, there's not much to get out of there other than X beta star and Q are showing up together. So somehow the misspecification matters. The degree of misspecification matters. Yeah.
Yeah, okay, wait, and just also going back to like when you were doing the example of like interpreting like the before treatment and after
Yeah.
treatment, you said that like you can't really have say like the 10%.
Yeah.
Like, is that like similar to saying like in an OLS, like if I start like at one point it doesn't exactly end up at another point it's like a it's
Yeah.
like it's just like the average, right? That's
I mean, I could have panel and have before and after, and I have the full distribution of people, and they all reshuffle. So the mean is going to change like this. So that's my OLS. But the people who are below the mean might be above the mean after. It doesn't change what the mean is. The same is true of the quantile.
So she's saying like if you're like above, it doesn't mean you're above.
Yeah, that's it.
So it's like the same interpretation with OLS.
Exactly. Which is why, but somehow it's like more.
People get confused.
There's more resistance.
Because like the order can shift, right? Like
I think people feel comfortable talking about somehow the average person as opposed to the average of the distribution. Okay. And so they want to maybe talk about the quantile person, and then it really doesn't work. But it's the median and the quantile. There's no. It's not lesser in any way, and you're not less talking about specific people in any way. Like.
Yeah. And like if the slope isn't different, right? Like it's meant to like cross, right?
Oh yeah, this line if you keep going.
Yeah.
Yeah, so that's not good, right? Yeah.
So like, is there like a range we can only like extrapolate on?
Yeah.
Or, like,
Yeah.
Do you have like a rigorous way?
No, you get the data, and if the linear dimension is not too crazy, usually on the data they don't cross. But it's not uncommon that when you plot them, maybe you have like almost no data here or no data, and then you plot all the way until when they cross. Oftentimes you try not to present the plot that goes all the way there, but if there's data, you kind of have to. Yeah.
But so like, it's kind of like an art about like where you can extrapolate.
Yeah, but also like if you have x and x squared in your regression, then these won't be linear, and that might tell the fact that they cross when you don't put the power might motivate you to try the power. Yeah.
Are these slides going to be available?
Yeah, I can send them. Yeah. Cheers. Hi. analyze the following question. Are the weights somehow changing slower than the model? Meaning that models that are not too far apart are comparable. That would be the question for somebody. I don't think someone has asked that question. I think that would be worth one. But I don't know if it's trackable. If it's intractable, like, it would be, we'll do like first order, check estimation, like yeah. Yeah, thanks. Yeah. But so yeah, I never thought about that, but the fact that the weights might be changing more slowly than the model, that could be something one could talk about analytically maybe. And then model comparison might still make sense. Because actually, like, cross validation is not completely satisfying because it's still not it's still about the forecasting exercise, not the best approximation exercise. So yeah.
I was thinking, there's just simple things that we wrote this in. Generative model.
Yeah.
But so, I was asking about restrictions on this one because it seems like, if I were generating directly from X and the conditional, I have very little restrictions, right?
Yeah.
For Y given X.
Yeah.
I pretty much don't need to impose any cross restrictions across X for that to be a legit conditional distribution.
Yeah.
Like everything goes.
Yeah, yeah.
But here for the quantas, I just want to see what's the space. Like, where does this leave us? And I was thinking about just because I wanted to also see how would I do this as a Bayesian, like non-parametric Bayesian.
So.
Didn't Neil Shepard had a paper on this? Like,
yeah.
I was reading also on some of these theories.
Yeah, and actually some of the Alfred stuff, I think like in a sense you need some notion of monotonicity that's basically gonna make it such that the quantiles don't cross. So then okay, question, if you do that and you ask that there's no quantile crossing, I think maybe that's it. Maybe that's the full space. Yeah, because then you're gonna get the monotonicity you need. Okay, but now if X is random, what's the rigorous way of asking for that? For any realization of X.
Right, because if this one is for a fixed X, you definitely have monotonicity in the use, right? So that's
you have to. Yeah.
That's really cool. So that means this has to be monotone functions for
Exactly.
Something that is not going to quite make sense, but maybe a version of this. I stay with
like we want something like somewhere I would have thought maybe on the outside explication we fix the x, and then we're looking for a coupling like this, and then we're very close to a modern sport.
Because if not, and also if these were completely independent of this one, it's like you could just condition and solve. So you get like the OLS, you get just
For any given x, you want small u to be small y, big U to be big y. Yeah. So that's
something like this.
so that's like if you do all the quantas at the same time with non-tracé, you write that quantization problem, you take the dual, then you're gonna get that you're trying to do max u y. So you're trying to get the big ones together. You need the marginals to be whatever they are, and you're asking for indigeneity. Something like that. But so yes, so it's that, and the linearity I think is rooted in the fact that your company here, the transfer is set with beta, so you can back it up and you get the linearity this way. So that's kind of the paper that does that. Yeah. J'en viens tout ton temps.
Yeah. So it's easier if I don't plug my computer, no? Seems with this.
Ouais. So les slides sont done déjà.
Okay. So I was wondering about sometimes showing some code, but.
Ouais, okay, but
you actually plug your computer.
no, this is there.
No.
Yeah.
Never mind.
Okay. So I'm there. Chercher les- Ouais, en fait, je sais pas. Est-ce que je sais que les slides, il fallait les slides?
Okay. Yeah, thanks. Hi, everyone. I'm Pierre, so I'm going to talk about MCMC, Markov Chain Monte Carlo. So we have four sessions on that. So hi, everyone. Don't hesitate to interrupt at any point to ask questions. And so let's get started. So I'm going to talk about MCMC. I'm going to assume that it's not a familiar topic to you all, at least, but I've put stuff that are more advanced, some stuff that are more basic. So let me know when you want me to spend more time. So I'll talk about the very basic to begin with, the motivation. Then we'll talk about some examples of those algorithms. So it's a class of algorithms. There's many, and I'll just talk about some of the more familiar algorithms for the statisticians / econometricians. But I'll talk about the fact that it's a class of algorithms that was mostly developed in physics, and it has many other applications in chemistry, in molecular dynamics in particular. So just focus on I think, the ones that are more useful for econometrics. Today we'll talk about some of the outstanding questions, which hopefully we'll try to address in the next few days, in particular using so-called couplings. But today we'll talk about the basics. So the goal is to obtain samples from a probability distribution. So I'll denote by pi throughout sorry. Up. Talk about the task of obtaining samples from a probability distribution. So I know Guillaume mentioned R. You're more like R users or Python users. It's the same. Obviously, you can code in any language. In R, for example, the normal distribution would be available through the density function. It's called dnorm. And you can also obtain sample using rnorm, right? So there's a function already made for you, so you don't have to do MCMC. So the problem is that in general, if your distribution is not just a normal distribution or gamma or a well-known distribution that has a Wikipedia page, then the problem of obtaining samples is not super generic. It's not a solved question. And so there are many ways of obtaining those samples. And often we are not directly interested in obtaining samples. We're more interested in obtaining integrals, computing expectations or integrals. So here I denote by E h of x, the expectation of the variable h of x. So x would follow pi, and h would be a so-called test function. So to give an example, maybe you're interested in computing the probability that the distribution pi assigns to a certain set. So the probability that your test statistic is in the rejection region, for example, if you're doing a test. And so that would be, x would be your test statistic, but h would be the indicator that this test statistic is in a certain set, the rejection region. So in general, there's a function h. Maybe it's just the identity function also, that's a usual case, and then you're interested in obtaining the expectation of x. Okay? And so with different choices of test function, you access different aspects of the distribution, all the moments, for example, the variance, and so on. And so the notation would be, assuming the state space is continuous, so integral of h of x, pi of x, dx, so that would be a continuous state space, while the distribution pi would have a density, denoted by also pi, as an abuse of notation. But in fact, it could be that the state space is discrete. It could be that it's a mix of discrete and continuous components. Right? So using quite a generic notation that is supposed to encapsulate various cases that might be of interest. And so the general problem is called sampling or numerical integration. So how to numerically obtain those integrals. And generally, we resort to so-called Monte Carlo methods to do that. There are other methods also. And so why is it interesting in econometrics and statistics? So people may be more familiar with the problem of optimization because the estimators typically are defined as the solution of an optimization program, just like what Guillaume was presenting in the case of quantile regression. So in general, you could imagine M estimation, where you're trying to minimize the sum over the data points of a function of some parameter theta, so that would be the betas in the previous talk, and that depend on the data. That could be just y's or y and x's, for example. And so it's quite obvious that numerical optimization is useful in econometrics and statistics. It may be a bit less obvious why integration is also helpful. So I'm going to give a few examples as to why I think optimization is helpful also in combination with integration. So in particular, it could be that your objective function, the little m function here, involves itself an integral, for example, over latent variables. Right, so itself, the m function might involve, so it might be, for example, a log likelihood, or the minus log likelihood, but the likelihood itself might involve latent variables. So for example, I'll give some examples later on. But there are all classes of models, such as state space models, for example, in time series that involve latent variables. And so then you might have an integral that you don't know how to solve exactly, and that might require some numerical integration. And so then you may be familiar with expectation maximization as a way of obtaining the maximum likelihood estimators in models that have latent variables. And in expectation maximization, you would alternate between essentially integrating the latent variables, u, and optimizing over the parameters. And that's only useful if you don't know how to do that integral analytically. Otherwise, you can just think that you have this, there's an integral here, but you solve it, you have just a function of theta, and you maximize that. But sometimes you don't know how to obtain that integral exactly. You don't have an analytic form from it. And so then you resort to, for example, the EM algorithm, which itself, in fact, can be seen as an optimization problem over two components, the parameter theta and a distribution Q, which is a distribution of that latent variable. So there's a way of seeing, so this is a bit of a complicated optimization problem now because one of the coordinates is a distribution. Okay? But so the EM algorithm is trying to do at every step an optimization over Q given theta and optimization of theta given Q. There are references here. Okay. So there are also estimates that are directly defined as expectations. So typically in Bayesian inference, for example, if you're familiar with Bayesian statistics, you would put a prior distribution on the parameter space. So the parameter now is a random variable. So prior distribution typically is a way of incorporating some information that you have prior to the data into the problem. So maybe because you had done some previous analysis of a similar type of problem that translates now into a prior distribution, so you know the parameters, for example, of your regression. After some previous studies, you know that they may be positive already, for example, and so you can incorporate that into the prior distribution. And then you have the likelihood function. You multiply the two, the prior density and the likelihood, and you obtain the posterior distribution. And then if you want a point estimate from that, instead of having, you have a whole distribution of parameters, but you may want to summarize it. And so then, for example, you can take the posterior mean, and that, by definition, is an expectation. So here are references in the econometrics literature that employ MCMC to obtain estimates that are defined as expectations. So far, so good? Okay, so hypothesis testing also, so typically you want to compute some p-value, and that is defined as a probability of observing a test statistic that would be at least as large as the one that you do observe under the null hypothesis. And so often, because you can resort to an asymptotic reasoning that tell you that this is a chi-square distribution or a mixture of chi-square distributions. So then again, you don't have to do Monte Carlo because you know a lot of things about the chi-square distribution. But believe it or not all test statistics follow a chi-square distribution. They may follow a very complicated distribution. And then again, in order to compute the p-value, now you have a numerical problem to solve. So those are two references. So the first one is lecture notes explaining various use for MCMC in hypothesis testing, and a recent one in analysis of stats. And I'm putting that just to say that even if you're firmly against Bayesian inference, and some people are very firmly against Bayesian inference, because this notion of prior distribution sounds like, for some people, it's against the objectivity of science, and so on and so forth. I'm mostly going to talk about the computation, so I'm more agnostic to that debate now, but it is a very big debate in statistics. But I just want to say with this slide that even if you're not interested in Bayesian inference, you may still have some numerical integration problems to solve. For example, in hypothesis testing, which is really on the opposite end of the spectrum than Bayesian inference for the statistician. Okay. So if you do want to do Bayesian inference, then typically you have integrals coming up for the posterior distribution, but also when you do model comparison. So for example, the BIC criterion, the famous model selection criterion, is an asymptotic approximation of the so-called marginal likelihood. So that's the denominator when you do Bayes formula with the likelihood and the prior. And the denominator itself is used as a model selection in Bayesian inference. And so sometimes it's convenient to do the BIC, so the asymptotic approximation when you have a fixed number of parameters and a lot of data. But in some other cases, maybe you don't have that many data points or the parameter space is very large, then BIC is very inaccurate, and you may want to actually compute directly that marginal likelihood. So this is, again, a reference. I'll try to put reference in econometrics more, assuming you're more in econometrics than I am, just to say that there is a lot of econometricians interested in those Monte Carlo questions. Okay, so actually I was also trying to link with causal inference in a desperate attempt to connect with the different parts of the title of the summer school. And so it turns out there's an active also research in MCMC, in causal inference, and that has to do with trying to find directed acyclic graphs that may be compatible with the data, because typically there's many of them, not just one. So finding the one point estimate may be a bit misleading. You may have lots of different graphs compatible with the data, so you may want to average over all those graphs instead of selecting one in particular. And then the Bayesian approach is a way of formalizing this sort of model combination, if you want. So there are papers, for example, operating on the space of direct acyclic graphs or different representations of it. So here are some references. And in the potential outcome framework, then you may want to do Bayesian inference again. And so Here are papers arguing that some recent causal inference competitions, the winners of those competitions have employed Bayesian non-parametric approaches, which again in practice means running some Monte Carlo algorithms to obtain the numerical answers. Okay. Don't ask me too many questions about the content of this article. Okay, so taking a step back, the Monte Carlo methods originate in physics, very much in the sort of Los Alamos, Oppenheimer type of setup. And it was a realization that a lot of computations cannot be done exactly, large sums, integrals, but using random variables, you can usually get a reasonable estimate of the quantities of interest. So I'll mention the original paper introducing the first MCMC algorithm in a few slides. And you can find now entire books dedicated to the problem, such as the Handbook of MCMC. The reason why it's popular is that in some sense, when you're integrating over a large dimensional space, Monte Carlo methods achieve the best possible rate of convergence that you can hope for. So there are results, for example, in Novak that says that compared to all the other ways that you could go about numerical integration, Monte Carlo is going to give you the optimal rate as the dimension goes to infinity, and assuming that you don't know anything about the test function, which is not true necessarily in practice, but in some sort of limiting complicated regime, this is the best way of doing numerical integration. So other ways of doing numerical integration would be, for example, if you have a one-dimensional integral, you want to compute the area under a curve. You know, naturally in high school, you may decide to grid the space, obtaining, for example, equidistant points on the space. You compute the value of the function there, and then you're going to approximate the volume, the area under the curve by for example, the volume of a sum of rectangles. Okay, and as you put more and more points, it will converge to the area under the curve. And you can see here that the smoothness of the curve will have an effect on the precision of your estimate. Right? You need more points if your function can go and wiggle about everywhere. Okay? And so in dimension 1, in fact, you should not do Monte Carlo. This will not give you the best rate of convergence. This equidistant point method would probably be better. It would converge at a rate of order 1 over the number of points, whereas the Monte Carlo method would converge at a rate of the order of 1 over the square root of the number of points. Okay, so in dimension 1, you should not use Monte Carlo. But this Novak paper, that is a review paper on the problem, would tell you that if you were in a d-dimensional space, where of course doing grids usually involve a lot of points, right? Exponentially many points, then it would be better to do Monte Carlo than any grid-based methods. Even though they are very smart grid-based methods, I must say. So if you're in dimension 5, for example, it's kind of up in the air. If you're in dimension 2, probably still smart grid-based methods are better. But as far as I know, in dimension more than 10, quite often in econometrics and statistics where the dimension corresponds to the number of parameters, then Monte Carlo achieves the best results. Okay. But it's not by any means the only method. So recently there was also a lot of interest, there is a lot of interest in the links between sampling and optimization, so I'll give a few pointers on that. Because sort of naively people thought maybe optimization is fundamentally simpler than integration. It's faster to obtain the MLE than to do Bayesian inference, for example. In fact, it's quite a complicated question, and so there's been a lot of interest in that question, trying to compare the difficulty of solving the optimization problem numerically and the difficulty of solving the numerical integration problem. So I'll try to give a few pointers along the way. Okay, so Monte Carlo methods are algorithms, so there's going to be some inputs, outputs. There's going to be some tuning parameters often that we'll have to choose. So we'll try to think about optimizing the performance in a way, and the performance will have to do with the cost of running the method, and then the precision of the output, the precision of the estimate. So inverse CDF transform, Guillaume mentioned it. So if you have, you want to sample from pi, obtain x from pi, and maybe you have the quantile function, so I'm going to denote it by q, and you plug a uniform sample in that quantile function, and that is distributed. If this is the quantile function of pi, of course, then that is distributed according to pi. Okay, so you could say, okay, problem solved, then why are we doing anything more complicated than that? Any guess, again? Why may we not do always this to obtain samples?
You won't always have such a closed, nice form of pi that you can
Yeah, we may not have access to this, and in particular when the distribution is not in dimension 1, even defining this becomes more tricky, right? The multivariate quantile functions. In fact, a lot of definitions of multivariate quantile functions that are useful, for example, in multivariate quantile regression, will not be such that if you apply it to a bunch of uniforms, you will obtain a sample from pi. Okay, so that's a problem. So there's a question of what kind of inputs are we going to give to the Monte Carlo algorithm. So if we want to sample from pi, we need to of course, we need to encode some knowledge about pi into the algorithm, right? So in this algorithm, which I call inverse CDF transform, so inverse CDF because the quantile is the inverse of the CDF, the cumulative distribution function. So that's where pi comes in the algorithm. It's in the choice of the function. Generally, we're going to talk more about algorithms that take the density, so the PDF, as an input. So we're going to assume that we are given a pointwise evaluator of the PDF. And what we want is use that pointwise evaluator and in an algorithm somehow and obtain samples. Okay. But it could be different. For example, there are algorithms that operate with only access to pointwise estimators of pi of x. If you have non-negative unbiased estimators of pi of x, there's a generic algorithm called the pseudo-marginal algorithm that will yield samples from pi, for example. But for starters, we just assume that we have access to an evaluation, a function basically like dnorm for the normal in R that gives you a pointwise PDF evaluations, at least up to a multiplicative constant, as we say. There are other methods, so I don't know if you're familiar with rejection sampling, for example. Does it ring a bell? Yeah. So for example, if you want to sample from the gamma distribution, like R gamma in R, depending on the choice of the parameters of the gamma, there are two parameters of the gamma distribution, then depending on the specific values, the best known methods to obtain samples are so-called rejection samplers. So in rejection samplers, do just a graph. So you have a distribution, for example, it may look like a gamma. It may look like a gamma to you. It's okay. It's like a gamma. That's some gamma, alpha, beta. Okay, so if you know of a distribution that is above this curve, or this function, the density function that is above, and it could be, of course, that one of them is not normalized, because otherwise they may need to cross, but it doesn't matter really the normalization. So suppose that this is a constant m times the density q of x for some distribution q. Then what you can do is sample basically uniformly under the curve m times q. So how do you do that? You sample from q. So you choose a q that you can sample from. You sample from q. So that gives you the x values here. And to obtain the vertical values, the y values, you sample uniformly between 0 and m times q of x. So you obtain those crosses. And then you decide to retain only the points that are under the gamma curve. And those points, if you look at their x values, they are distributed according to the gamma distribution. That's called rejection sampling. Okay? So you're losing a bit if your function n times q is very far away, because then you're going to reject a lot of points. So you try to find the m and the q such that n times q is as closely as possible above the distribution of interest. Okay? And that can be very complicated, again, in high-dimensional spaces, to find this sort of good approximation, good global approximation of the target. But sometimes it's still feasible. For example, again, if you have a lot of data, you can do asymptotic reasonings. In Bayesian inference, the posterior distribution, according to the so-called Bernstein von Mises theorem, will be approximately normal. And so you can then come up with, say, some multivariate students that could be a good global approximation, but above to the normal, the posterior distribution, and then do rejection sampling. But it's pretty rare. So usually people do that, again, in small dimension. And then importance sampling. Anyone knows about importance sampling? Yes, more or less? No? No. Yes? Do you want to explain what it is? No.
That's like where we take the, we want to produce these weights. Sorry,
Okay. Well, it's basically the similar setup as radiation sampling. You have a global approximation Q. You sample from that, but maybe you don't know of a constant M to choose such that, because here the M should be such that pi of x divided by Q of x should be less than M for all x. And that may be not so obvious to find this. I mean, that's kind of an optimization problem over x. In fact, you want to maximize this ratio, and if it's finite, then maybe you can find the upper bound. But if you don't want to do that, you can just sample from Q independently, so IID from Q. And then you can define weights. So for each x, and that will be pi of x divided by Q of x. So you do a change of measure, basically it's a change of measure formula. So you sample from Q, but you reweight the points according to how likely they should be under pi, but also you want to downweight the points that you sample a lot from Q. Otherwise they're going to be overrepresented. So it turns out this ratio is the right one, and that's quite easy to see because you can, if you have an integral with respect to pi, you can divide and multiply by Q, assuming it's never 0. And so then that means that you could have just another Monte Carlo problem where Q now is what you sample from, but you have to weight the test function with the ratio pi over Q. So that's all it is. And the benefit is that you don't need to know about this M. But of course, the downside is that you actually don't get samples from pi, you get weighted samples. Okay. Weighted samples. Yeah.
If we were to try to do rejection sampling, but we mess up what M is, and suppose MQX is now going to be, for some values of x, lower than here in the case of the gamma distribution, do we know the result that we get? We know it's not going to be from gamma, but do we know something about it that would be useful?
Yeah, so you have to specify what you do then so what do you do then when, so you have chosen an M, but it may not be the right one. So it may be too low. So the picture looks like this now. Maybe you have a point here. So definitely you accept it, but you basically never reach that area here. So you're going to miss basically some points where there should be more points. Yeah. Maybe you can work out, to some extent, the distribution that you are sampling from when you do that. Yes. It's going to involve, I think, some sort of pointwise minimum. Up to a normalizing constant, it's going to involve some pointwise minimum between pi and m times q, which then you can relate in total variation distance probably to pi. You can probably say something about how distant it is from pi in total variation, because the total variation is the area under the PDFs. So you can say something, I imagine. Yeah?
Then you get a flag, right? You have to run this to evaluate the Q and the pi. So you know when you've drawn that if that your M is too small.
Yes, in that case you would know, but the problem. Well, the problem is that you don't evaluate pi. Typically, you obtain something up to a multiplicative constant proportional to pi. And because you don't know the constant, typically you don't know if you're in that scenario or not. So you need to know sort of a priori that your m is above that ratio. You know that your m will be too small relative to the proportional function that you're using. But then, yes, you will probably, I agree with you that probably there should be some flag that tells you there's a problem. Yeah.
You could do this up to a constant on pi that goes into the m somehow, so that you may not have a flag.
Yeah, yeah.
You evaluate the true pi.
Yeah.
Okay, so from inverse CDF to importance samplings, there's like a gradual like relaxation of conditions.
Exactly.
So I assume from inverse CDF to rejection sampling, it's kind of one time, I would assume, like, right?
So that's a good point, actually. Usually the inverse CDF, it takes you, in univariate settings, it's always applicable, in a sense, numerically, because you can numerically inverse the CDF. The CDF, you can numerically integrate the PDF to get the CDF. So even from the knowledge of just the PDF, in dimension 1, you can numerically integrate it to get the constant. You can do everything and do inverse CDF transform all the time. So it's only a runtime question, the reason why R gamma doesn't do inverse CDF, for example. It could be doing always inverse CDF transform, but numerically it can be more advantageous to do rejection sampling.
Okay. And for importance sampling, like, is it like asymptotically like approach like the desired pi, or like how fast?
Yeah, so that's a good point also. So in some settings, if you're interested not in obtaining a sample from pi, but just computing an integral, you don't have to go to the intermediate step of obtaining samples from pi. So it could be that it's faster to do importance sampling, where you weight everything instead of rejection sampling, where some of the points are gone, basically, are wasted out. So it could be that you're better off doing importance sampling than rejection sampling for the same Q, the same function Q. In fact, it could be that it's better to do importance sampling than perfect sampling, because, for example, suppose that your distribution is like this, but you're interested in computing a tail area here. So then sampling from pi is going to give you few points where you want, okay? Whereas maybe you can introduce an importance sampling distribution that's sort of better placed. So there is some work, so in Arthur Wen's book on Monte Carlo methods, which is good, which I should put a reference on. When it's on his website, there are all the chapters. And there's some examples where it shows that, for example, if you were interested in a tail area, the best possible distribution puts half of the points inside and half of the points outside. So it's sort of located at the threshold, basically. Okay, so yeah, importance sampling can be something that you prefer to do compared to obtaining samples from pi. Yeah.
In all these scenarios, we have to have some sort of knowledge. At least we need to be able to evaluate pi effects
Yeah.
at this axis, right?
Yes. Or up to a multiplicative constant.
Okay, if we can do that, I feel like we can already sort of non-parametrically recover this pi
Yes.
somehow.
Yeah, I mean, so I guess fundamentally, if you know the PDF of pi, you know everything about pi. It's characterized by the PDF. It's characterized also by the moment generating function, right? But if I give you the pointwise evaluator of the moment generating function, you may not know how to compute the integral with respect to the PDF. But it is true that it's not surprising that all the knowledge is there. But for example, here's an open question, as far as I know. If you are given pointwise evaluation of the gradient of the log density, there should be all the information about the pi in there as well. Because you are losing the multiplicative constant, but you know it integrates to 1 anyway. So if you know that everywhere, you can do principle, there's only one pi that corresponds to this function, right? And yet, there is no Monte Carlo method that I know that takes only this as an input and even asymptotically recovers pi. It's possible that there is one, there will be one, but it's not known. Whereas, for example, you can optimize, of course, with gradient descent and get the maximizer of pi of x with this. So and so indeed, you could sample, you could do a grid, evaluate pi everywhere, and then non-parametrically interpolate between the points in the grid, and in the number of points, you will recover everything about pi. It's just not the most efficient thing to do in large dimension. We good? Okay, so what we're going to do is we're going to construct Markov chains. So that's a way of going beyond what we can do easily with importance sampling and rejection sampling. In particular, because we won't have to know about a general good approximation of pi on the whole space. So maybe we'll rely only on sort of local information about pi, local perturbation, in order to obtain globally a sample distributed according to pi. So schematically, we're going to sample first anywhere. So we're going to start from some distribution pi 0. It could be, for example, the origin in the state space, the vector of zeros. And then we're going to progressively change x0 to obtain x1, and then change x1 to obtain x2. We're going to do that randomly. So that's going to define a Markov chain, a Markov process. So Markov in the sense that when we're going to obtain x2, we're only going to modify x1 and forget about what comes before. There are some other methods, for example, so-called adaptive MCMC methods that employ the whole history of the points that we have generated. But we're going to focus on the simpler Markov chain case. And we're going to do that capital T times to obtain xt. That's going to be approximately distributed according to pi if we do things properly, if we design the algorithms adequately. And in a sense that will be to be defined more precisely later on. And so here we're going to work on discrete time in passing. Of course, you could, in principle, operate on continuous time. And there are, in fact, algorithms. For example, in the Monte Carlo literature recently, there were a lot of piecewise deterministic MCMC algorithms. There's a reference here, and those operate on continuous time. It doesn't have to be... so the state space could be discrete or continuous. The time could be discrete or continuous. But mostly the time is discrete in that literature. Okay, so there's going to be various questions we're going to try to touch on in order to, again, understand the inputs and the outputs of those algorithms. So in the output, the simplest way of running those algorithms is to do a long run. So you basically do those steps for as many iterations as you can. For example, you leave the office at 5, you run the algorithm, and you come back to the office at 9, and it has done 2,000 steps, and so that's your number of steps for today. Okay? But the validity of the algorithm would typically rely on this t, this number of steps, to go to infinity. So you could be tempted, especially in the era of parallel computing, to go on Amazon Cloud and to ask 1,000 machines to perform this in the same amount of time. So again, from 5 p.m. to 9 a.m. the next day. Each of the machine still does approximately, say, the same number of iterations that you would have done, but now you have 1,000 chains. Okay? So that should be helpful for something. And so in particular, if you average the results over the different chains, so the IID across the different machines, so you're going to reduce the variance by the number of machines. You're going to divide the variance by the number of replicates that you're doing. The problem is the bias, right? So you're going to kill the variance by averaging over independent copies. But if there is a bias, averaging independent copies will not reduce it. Right? So that's the problem. So that's why you don't do a million times one step, and you still want to do enough steps. Right? It's the same with optimization. Right? Typically, the guarantees are obtained iteratively. And that's a big problem at the moment in particular because the machines are not getting much faster, but we have more of them. So in terms of clock speed, the number of gigahertz, that's sort of more or less proportional to the number of iterations you can do in a given time. that hasn't been going up very much lately. So that was different in the early days of Monte Carlo, where you could just wait for the next year's computer to do twice as many iterations as this year's computer. And so that was fine in the sense that the algorithm would rely on asymptotic regimes like that. But nowadays, you would like to leverage more and more machines because there's really fundamental limits in the clock speeds.
I was going to ask, related to if you long run versus many short runs, if you don't mind going back to the previous slide.
Yeah.
So we started from x0, applied random perturbations, got x1, do the same thing all the way to xt. For t large enough, xt would be drawn from pi. If we took a look at x cap t minus 1, let me now construct a different MCMC chain that where the new pi naught is going to put all its mass on this x cap t minus 1. So the first sample of this new chain is going to be x cap t minus 1.
Mm-hmm.
If I were to apply the same sort of random perturbations to x cap t minus 1 as I did in the original chain, it feels like the new x1 that I would get would be the same as the x cap t that I would get in the original sampler. So
Yeah.
it would be then the case that the large enough cap t in this new sampler is 1.
Yeah.
Okay.
But you will get only one sample from that.
Right.
So for example, that's so just to be clear, so if you look at the trace of the chain, right? So you start from say x0 and you run a Markov chain, so trajectory is like this. And xt, your hope is distributed according to the distribution pi. Now, if you start from xt, then it's like starting from pi. But if you started many, many chains from xt, they would not give you IID samples from pi in one step. It would give you always, from there, marginally it would be from pi. But if you start independent chains from there, they would probably be after one step quite close to xt. So they would not give you a whole sample from pi. You see what I mean? So having one sample is only going to help you warm start one chain, in a sense. Okay, so this problem of bias, basically, the bias that comes from not having started from pi independently, having started from pi 0, is sort of the main problem in trying to parallelize MCMC. If you could sample from pi from the beginning, you could do that on many machines. That has been well recognized for a long time. Okay, so that's I'm announcing this as one of the problems we'll try to address with this so-called coupling machinery. So we'll see a classical algorithm called coupling from the past. And that's from 1996 that employs coupling to obtain perfect samples, but from Markov chains. And then we'll move on to more recent estimates that are due to Peter Glynn and Chang-Han Ri in 2014.
Just another clarification question. If we are able to start sampling from pi at the get-go, then is it, if I'm understanding correctly, that we don't have to work with this finite time bias?
Mm-hmm.
So if I were to run one chain, get x cap t, and then start parallel chains from x cap t as you were describing there, would that take care of the finite time bias, or do we still worry about finite time bias?
No, so it's quite subtle. It's hard to write. But if you have xt that's distributed according to pi, and now you run say xt plus 1 to xt plus 1 r, you sample them from what we're going to denote by p of xt dot. Okay, so you do one step of MCMC starting from xt, but you do it many times in parallel. So marginally, they will all be from pi. If you do it once, or if you do it r times, it's the same. They're all from pi, but they're not independent. They're not independent from pi. And so, in fact, they could be all very, very similar to your xt, and pi could be very different from a Dirac mass at xt. Right?
Maybe I misunderstood the question. I thought the question was, what if we start
if you draw every time the starting point independently from pi, then after one step, you get a point that is still distributed as pi, but now it's independent from the other. So that's fine. So if I draw independently, even from x0, another point, and I have another trajectory, and now I get another xt, and those two xt's will be more or less independent points from pi. But the problem is if you start always from the same guy, you still maintain marginally the fact that it's distributed according to pi, but now of course you can imagine that they're not going to be distributed far away from in one step from the previous point, so that's not going to solve your sort of integration problem. But if your point is only to get, if your goal is to get non-independent samples from pi, then that's fine. But typically that's not what we want. So it's quite subtle, but probably we'll go back to that, yes?
So, for your second run, can you start from the same x naught, but just set a different seed?
Oh yeah. Then if you do a lot of steps, it's probably the same if you start from the same x naught or a different x naught.
Then can you start from the same xt, but just set different seeds, and then after like a certain amount of time, it's like pi.
Oh yeah, you're right. So if I do, again, a lot of steps, then they will sort of disperse and be nearly independent from pi. The problem is one step now, unless your MCMC algorithm is so good that it only requires one step.
Is the number of steps that's needed for the new point to the ID less than
That's a very good point, yeah. So I guess there's two things. There's getting marginally from pi, and there's sort of forgetting the initial point.
Yeah.
And it's true that technically you could define those things differently, but then for typical Markov chains in MCMC, essentially it's going to be the same time to go from anywhere to pi or to be independent of your starting point. But it's true that it could be different for other processes. Yeah.
So for the long run, like you summed up all the different time steps.
Yes.
But for the parallel run, like
I didn't.
just sum up all the time steps as well.
Absolutely, yeah. Yeah, you're right. You could average over the times and then average over the copies.
Yeah.
I was just saying that if you were to do R going to infinity asymptotic here, in a sense you would always get, you wouldn't have to even average over the times because you would get perfect precision if T is large enough from just the last guy of each chain. But it's true that in practice you'd want to not waste all those points before, and so you'd average over time, and then you'd average over the repeats. Okay, so let's try to come up with examples. So this is kind of an exercise, yeah, Guillaume?
Yeah. Actually, what I had for so if I'm just trying to get independent samples, I can go along the chain with long enough that I think
yes.
my next example is independent.
Yeah, you could imagine that if the time in between is very large, they're kind of independent of one another.
Is there a formula we think about how whether I even want to do that or how I want to do that if I'm interested in the integral?
Yeah, that's a good point. So that's called thinning in MCMC.
Right.
Thinning the chain is to retain only some of the points along the chain.
Like I would want to keep more points if I care about integral than if I care about producing a sample of points from it.
Yeah, absolutely. So in fact, if your goal is precision of the average over time, then there is no point in dismissing samples. Right? You should keep all of them. But if the question is, because your memory is limited, for example, or maybe your test function h is very expensive to evaluate, and so in that case, it's better to do a lot of steps before you evaluate it, and to keep only, so there's actually a very good paper of Artowen on this. But typically, h is instantaneous to evaluate, it's an indicator function, and running the chain is very long. And so it's better to keep, especially you can compute a sum like this on the fly, right? So you don't need to store anything. So if your goal is the approximation of an integral, there's no memory issue. But if your goal is to find, you run 1 million points, 1 million iterations, and you want to best 1,000 points that are representative of pi, you should not keep the last 1,000. You should sort of equispace them. It's called thinning. Yeah. Okay, So here's an exercise. And so, you have a distribution which is non-standard, still in one dimension. How do you obtain sample from it? Maybe you can come up with a good global approximation and do rejection sampling, for example. Or you can start from a point, x0, and then try to think about how you're going to construct x1 and then x2 and then x3 and so on, in such a way that if you do enough iterations, the samples are going to be distributed according to pi. It could be a good exercise to really, even if you know already a bit about MCMC, to restart from there and think about what can you possibly do. So this distribution, if you plotted the curve, it looks like this. Kind of a wiggly perturbation of Gaussian. And you start from x0. Okay, so we're going to try to come up with a Markov chain that will converge to pi. So do some sort of local modification of x0 first. So we want to move. So what can we do to move? Propose a move. Yeah, you could imagine, let's sample, we're going to call it x star, centered at x0, and with some tuning parameter sigma square. Right, so maybe we run it and then we end up here. But if we are saying x1 equal x star and continuing to do that, it wouldn't work, right, obviously, because we have not used pi anywhere first here, so that's a bad sign. And also it's a random walk, right? So we know that in fact it would not even have an invariant distribution, it would sort of diffuse in the whole space. And so what we can do is we can propose these points, but not necessarily define x1 to be that point. We can decide if x1 is going to be that point or not. Okay? So that's going to be the so-called Metropolis-Rosenbluth-Taylor-Hastings algorithm. So most people call it just the Metropolis algorithm or Metropolis-Hastings. But I call it this instead. So I'm going to talk about why later on. It doesn't catch. I've been calling it for a few years. It's not sticking. But, so we propose, okay, so we just did that. We're proposing x star from a proposal distribution, which could be just a normal centered at xt. So now we are at time t, and we're imagining how to construct t plus 1, xt plus 1. And what we're going to do is either we're going to set xt plus 1 equal to x star, or we're going to define xt plus 1 to be equal to xt. So there's always going to be an xt plus 1. So all we're going to do, one step. It's not like a while loop. We're doing one step. Okay. But just the new point could be exactly the same as the previous point. So the trajectory could have some sort of flat horizontal lines. And what do? We accept these points if, so with probability given by minimum between 1 and this ratio. So it's something uniform and compatibility to this ratio. And this ratio, it has some pi in it, so that's good news. We're using pi now. It has a ratio of pi's, in fact. So pi evaluated at the new point, the proposed point, and pi evaluated at the current point. So you see that because it comes in as a ratio, any multiplicative constant here would cancel out. So we don't really need to know exactly pi, but any function proportional to pi would result in exactly the same decisions to accept or not. And we want to also take into account the proposal distribution, because if we are more likely to propose some places, then probably we should discount the acceptance of those points. And so if you actually sample from a normal center at the previous point, so you have some symmetry, right? And so this ratio of q's would cancel out. So we would accept or not only based on the ratio pi of x star divided by pi of xt. So basically, if pi of x star is larger, you will accept. If you propose a point that has a larger density, you will accept. That's not the case here. Here we're proposing a point that has a smaller density. And we may still accept. Okay? So in a sense, that's a different with optimization, with basic optimization. With optimization, we try to find a better place. But here we may want to accept a point which has a lower density, because we want points everywhere, right? We want more points where there's high density, but we also want some points, especially if you're going to have a lot of points, some of them should be in regions of lower density. So this ratio sort of hopefully makes intuitive sense. It may be not clear why it's exactly this formula and not another formula. Right? It could be all sorts of formulas that would still be valid, fact, but this one is special, and so this is the one in particular exactly in that form. It's in the paper of Hastings in 1970. So the Rosenbluth in the name, Metropolis Rosenbluth Taylor Hastings, only passed away a few years back during COVID, but she was in her 90s. And she's the one who implemented it in 1953 on the MANIAC computer, so that's in Los Alamos. And usually in algorithms, it's the person who implements it who really understands what's going on. So I think it's probably the person who really understood what was going on in the 1953 paper, but her name was sort of dropped out of the people usually call this the Metropolis algorithm. She's the first author in that original paper. And that's the guy who had the computer. That's the director of the lab. So his name was automatically in every paper. Apparently he didn't do anything on that particular paper. But he's a famous physicist who did a lot of other things. But Rosenbluth did the implementation, so probably she understood what was going on. She was also amazing in different ways. She did the Olympic Games in fencing for the US team, and she was one of the first few people to get a PhD in physics. She was the 5th in the US or something like that, among women in the US. Okay, so that's the name of the paper, Equation of State Calculations by Fast Computing Machines. So Metropolis, Rosenbluth, Taylor, and Taylor. And that last Taylor is a famous physicist who is in Oppenheimer. He's the bad guy in Oppenheimer, who's betraying Oppenheimer and calls him a communist, and he gets into all sorts of problems. So that's the last guy in that paper. So they're all working on all sorts of Monte Carlo methods, and this one is the first to propose a Markov chain approach. Where you don't come up with a good global approximation, you start somewhere, and the problem has to do with packing. So you have a square, you want to sample so-called hard disks, so those are disks with a radius, and they cannot overlap. Right? So you want to put a certain number of those balls in a square, but they're not allowed to overlap. So in the problem, there was a certain choice of radius. Let's say that the square has length 1, and they were operating with 224 disks. And so you imagine that if you randomly sample centers for those disks, there's a very large chance that 2 of them will overlap, so you will not get a valid configuration. So instead, let's start from this packing. So you deterministically obtain the packing, which is basically disks that are adjacent. Take the least amount of volume, and then you're going to try to modify them to move them sort of locally. So you're going to take each of the balls, and you're going to propose a new center for it. And if it doesn't clash, it doesn't intersect with the other balls, you accept. Okay. So the original problem was already quite hard, I would say, because in fact the dimension is 224 times 2, because each ball has a 2-dimensional XY coordinate. So it's quite a large dimensional problem. And they did 64 iterations. They explained in the paper that it took already days. And that was that. There was no sense that it was enough iterations. There was more like the number of iterations that they could reasonably do. And so that's what they did. And they do also, they do a run with like 32 iterations, 64 and 96. And they see that the estimate doesn't change so much between 64 and 96. And so they are sort of happy. But it could have been that they found a sort of local mode. They wouldn't. And so in fact, what's interesting about this, I think, is the convergence analysis of this particular algorithm, the very first in the literature, is nowhere. So the closest that I find is this paper by Diaconis, Lobo, and Michel that analyzes a simpler version, in fact, of this algorithm. But the analysis of the original algorithm is an open question. Like how many iterations does it actually take for the algorithm that they propose to reach stationarity? So the interest has moved on because now people use different algorithms to solve those kind of problems. And so it turns out that no probabilist has solved exactly this question. Okay, so the general idea, and what we've just seen with Metropolis, Rosenbluth, Taylor, Hastings is a particular case. There's many other constructions to obtain a convergent sequence of points that will go to pi. And the general idea is that you will try to obtain a fixed point iteration on the space of probability distributions. So you will change the distribution in a way that you know that if you are arrived already at pi and you do one more step, you would remain at pi. So there would be some sort of fixed point phenomenon. So if you write pi t, the marginal distribution So you start from pi 0, then you do one step, and marginally, the distribution of that point is pi 1, and then it's pi 2, and so on. And you denote by px dot the conditional distribution of xt plus 1 given xt equal x. And that's the same for all t, because we say we use the same algorithm repeatedly, right? So it's a homogeneous Markov chain. So capital P here describes the distribution of the next point, given that the current point is at little x. Okay, so by definition, we can write the marginal distribution after one step as what happens when you start from pi t and do one step with p. So in terms of integrals, the mass of pi t plus 1 around px prime, you integrate over what would have been the previous step. The previous step is according to pi t, and then you did one step to arrive around dx prime. So if you want pi t dx px dx prime here on the right, that's the joint distribution of two consecutive steps. So if you integrate over the first, then you end up with the marginal of the second. That's it. And so by construction, those MCMC algorithms are pi invariant. So they're constructed in such a way, so this ratio that we've seen in the acceptance decision is exactly such that if you were already distributed according to pi, after one step you will still be distributed according to pi. Right? That's not enough to guarantee convergence to pi, but that's a good start. That's a good start. Okay, so you can say more about the transition kernel, so this capital P, for the specific metropolis algorithm. We can write it in this way, so it looks a bit nebulous perhaps. So there's a chance that you remain at the same point as before. That's if you reject the proposal. So with a certain probability that depends on where you are, R of x, so that's the rejection probability, your next point is following a Dirac mass at x. Otherwise, it's distributed according to Q, but weighted by this propensity to accept those points. So that's alpha, that's the acceptance ratio, basically. So R of x, you can write it in terms of Q and alpha. So that's R of x is the probability of rejecting a point if you start from x. So it's 1 minus the probability of accepting a point, and that's the probability of accepting a point is, you're going to propose them from Q, and then you're going to accept them with the given ratio. And so in fact, it's a probability. So you have this ratio of pi's, and then there's the ratio of the Q proposal. Dx prime. So the minimum 1, is that clear where it comes from? It wasn't in the algorithm because we don't need it in the algorithm. Right? If you draw U from a uniform, it will be less than 1. But the probability of accepting cannot be just this ratio because this could be larger than 1. So the probability of accepting has to be the minimum between 1 and that. Okay, so now you can check that indeed this satisfies the so-called detailed balance condition. So that's pi of x px prime is equal to pi of x prime px prime x. And that in turn implies the pi invariance. So it's very easy to see the last point here. So if you have detailed balance, you have pi invariance. Because, so if you, pi invariance is the fact that pi of x prime is equal to the integral of pi of dx px x prime. Okay, so I'm going to write it more simply with pi of x dx. But if you have detailed balance, it's clear that this thing would then be equal to the integral of pi of x prime p x prime x dx. And so if you have detailed balance, you have this equal that for all x prime. So you can integrate. And then when you integrate, you realize that you're integrating just this x here. But because p is a conditional distribution, it integrates to 1. So you're left with just pi of x prime. So you've just shown pi invariance. It's a good exercise to do. It's kind of nearly automatic. So that's the way that MCMC algorithms are designed typically. You try to get detail balance, and then you know automatically you get pi invariance. Most algorithms, like 99.9%, will satisfy detail balance. There are some exceptions. You can be pi invariant without satisfying detail balance, but mostly it's constructed that way. So it remains to check that this ratio is, the acceptance probability is such that you do have detail balance. Okay, so because of the form of P of x, x prime at the top, it's obvious that for x prime equal to x, you will have detail balance. You have pi of x, then you have r of x delta, an indicator that x is equal to x prime. And so because you have an indicator that x is equal to x prime, you can put x prime or x as you want. And so you have the equality on both sides. What's not so obvious is that it's also the case when x is not equal to x prime. Check that. I think it's important just because this ratio is not, it's not magical. This acceptance probability really comes from having constructed it so that it satisfies this. And so you want to show in the case of x different than x prime, you have, you're in the right-hand side of the formula at the top. So you have this. Okay, so now you replace the form of alpha by what it is, so the minimum between two things. So you have the minimum between q of x, x prime, and this is going to cancel out something that was at the denominator. So now you have pi of x prime over pi of x, q of x prime x. Right, so now you can put pi inside as well, if you want. So here I just, there was a 1. There was a 1, a minimum 1, and the ratio. I put that q of x, x prime inside. So I have this. But then I can also put pi of x inside, so on both sides. So then I have this, and I can erase the denominator here. And that's basically symmetric in x, x prime. So you have detail balance, and so you have pi invariance. So at least if you start from pi and you do one step of this scheme, the point that you get is still distributed according to pi. So it could be different. So there are other acceptance rates that would satisfy this property as well. Interestingly, so in 1973, Esken was the PhD student of Hastings, proved that in fact this ratio is in fact the best in the sense that for a given choice of q, if you use this acceptance rate, you will have the best chance of accepting while still being pi invariant. And having the best chance of accepting, so the maximal acceptance rate, in turn, that's the theorem, leads to a minimal asymptotic variance for the estimators.
In the class bigger than detail balance.
No, I think looking at all the acceptance rates that are leading to a pi invariant, the detail balance condition.
That's a very small class. Because if I want detail balance and I'm looking for my acceptance probability in the natural system, I can almost derive. I think I can derive this.
You can derive it, but you can derive another one as well.
Okay.
So, for example, the Barker one. So there was some doubt because people were using either that one or this one. So the same numerator, but at the denominator you had the same thing plus the symmetric one. That's called the Barker's acceptance. So that also is valid, for example, but you accept less, and so you get.
And you have detail balance.
And you have detail balance. And there may be others. Yeah. Okay.
Can I ask a quick question just to make sure that
Yeah, yeah, absolutely.
Distribution, pilot T.
Yeah.
And you pass it through this integral that is defined by this partition kernel, and that spits back some pi t plus 1, right?
Exactly.
For each algorithm. So when you write the proofs of convergence, just like, what exactly do you show? You show that you look at the distance of pi t plus 1 evaluated suppose that these are actually PDFs, so I don't have to do the dx, so just have pi t plus 1 of x prime minus the true pi of x. And what do? You do the sup over the support,
yes.
take the limit, or are these things pointwise, or how do you think,
Just-
thinking about what type of statements you actually get from this?
Yeah, so tomorrow in particular we'll look at specific statements, but typically convergence in total variation, which is the integral of the difference between the PDFs, or in the Wasserstein distance, so the optimal transport type of distance, which is in 1D would be the integral between the CDF. So CDF, PDF, that sounds like the same, but it's convenient to work with. And then there are results in Kullback-Leibler, there are results in Prokhorov distance, and depending on the algorithm, whatever is more convenient. And of course, there are some generic relationship between the distances, but TV would be the most used metric in MCMC, I would say.
Yeah, so just in terms of the theorem would say something like, suppose that the kernel that you're using satisfies these pi invariants.
Right.
Then the limit of the total variation is pi t plus 1 relative to pi. T goes to infinity, goes to 0.
Goes to 0, that's the basic. But then, of course, you want to know the rate of convergence and all that stuff, yeah.
Okay.
And we'll see that we need more than pi invariance. So a very simple example. If P of x dot is the Dirac mass on x, so your chain is staying wherever it is, actually that's pi invariance, right? So you take a draw from pi, you do nothing, and you get a draw from pi. So clearly we need something more, right? But in fact, not much more. Okay, so there's all sorts of things that are interesting about this particular acceptance ratio. So it leads to the best. So I need to check about in which class. But somehow it's better than markers, but it's somehow supposed to give a good asymptotic variance for your estimates. It's also, in a certain sense, the minimal deviation from your proposal. So your proposal distribution that could have been the normal centered at the current point. So that's a Markov kernel, but it's not pi invariant. So you can imagine, okay, let's project that operator onto the space of pi invariant operators. So find the closest, the least, the smallest modification that you can do to it in order to be pi invariant. And in a specific sense of distance, in specific definition of distance, you do get again this Metropolis Hastings chain. So that's proven in Villela and Jacob in 2001, and it's used in recent proofs of convergence for variance of Metropolis Hastings. But the distance is a bit complicated, I would say. So it could be that, by the way, it could be that if you change, if you pick your favorite distance between two transition kernels, and you do the same type of projection, you find a new algorithm, perhaps. And here is really projection onto pi invariant Markov kernel. So it could also be that you find a kernel that is not satisfying theta 1 or line. But, so this distance, and so how do you compare the two different Markov kernels? So here it says that you look at the difference, assuming everything has a density. You look at some integrated distance between the PDFs, from x to x prime according to the two kernels, but you integrate that with respect to pi for the starting point. So that gives you a metric on the space of transition kernels that are pi invariant, or even not pi invariant. Okay, so we just talked about the most basic algorithm, the one from 1953. But in fact, the one from 1953, it didn't do exactly what I just said. So if you go back to that. So here the state space would be the x and y position of all the poles. And so you could say the basic application of Metropolis Hastings to that would be to propose, say, a Gaussian deviation of all of those coordinates at the same time and decide to accept or not. So that's not what they did. Quite intuitively, they delete one whole all, and then they sweep through all the balls like this. So this now would be called a Gibbs sampler. A Gibbs sampler is when you don't change everything. You go sort of component by components or blocks of components at a time. And that's convenient because it's easier to get a decent acceptance rate when you're looking at a smaller dimensional problem. So it's a way of dividing a big problem into lots of small dimensional problems. So that's called Gibbs sampling. And of course, there's a lot of questions now. People are still debating about whether you should do a random order of the updates or a systematic order of the updates, for example. Is there a best order of the updates to do? Of course, it's also not clear always that you should do the same number of updates for each of the components. So in the hard disk problem, everything seems symmetric, so why prefer one ball compared to another? But for example, if you're doing some sort of Bayesian regression, you maybe have some components correspond to the regression coefficients. Some components maybe represent the variance of the noise. Maybe it's a good idea to update many times the variance of the noise before you re-update the regression coefficients, for example. So there could be lots of tuning parameters involved in an efficient algorithm. There's also a systematic way of addressing a certain problem called slice sampling that operates with an augmentation of the state space. So for example, if you want to sample from this distribution with density exponential minus square root of x over 2, there's a very nice slice sampler that, so you could do what we've just proposed with normal deviations accepted or not. But you could do something where you introduce a variable u, which given x follows the uniform between 0 and pi of x. Okay, so you have the original problem, now you have a u, you augment the state space to include this u variable. And now you can work out analytically the formula for x given u. And you realize that in fact you can sample from that. I think if you work it out, it's a uniform distribution as well. And so now you can have an algorithm that alternates between updating u and updating x in such a way that if you just look at the x components, it will converge to pi. So this idea of like updating components at a time is quite powerful, basically, to address all sorts of problems. It's a good trick to have. Another classical problem is the probability regression model.
One quick question, sir. But in that case, in the previous example, we knew the pi of is constant, right?
Right.